Okay, so are you ready to dive into some, like, seriously cool physics today?
Always ready.
All right, great, because we're going to be tackling spontaneous symmetry breaking.
It sounds good.
And we've got this fascinating paper by Deutscher, Nahm, and Napiorkowski
Oh,
to
yes.
kind of guide our deep dive today. And they're exploring this concept in the context of Bose-Einstein condensation, which, is where a bunch of bosons decide to crowd into the same quantum state.
Yeah, it's like a flash mob of particles,
Oh, yeah.
all choosing to do the same dance move, and usually the lowest energy one.
Interesting.
So this paper dives deep, and they mathematically prove that in a system of weakly interacting bosons, Bose-Einstein condensation is directly linked to the breaking of a specific symmetry, the U1 symmetry.
So this isn't just like an intuitive idea or something. They've like actually proven it mathematically.
Yeah, they went deep with the math on this one.
I'm intrigued, but before we get to like all the nitty-gritty of the proof, can we just like back up a bit? I think it would be helpful to clarify what spontaneous symmetry breaking actually means. Like, what are we even talking about?
Absolutely. Yeah, so think of a perfectly symmetrical system, like a ball balanced perfectly at the top of a hill.
Okay.
The ball itself and the laws of physics governing its motion are symmetrical, right?
Right.
But the moment that ball rolls down, it chooses a specific direction
Right.
and spontaneously breaks that symmetry. So the system's state no longer reflects the symmetry inherent in like its governing laws.
Okay. That image like really helps. So in this case, what's the ball and what's the hill?
So the ball is our system of bosons.
Okay.
And the hill represents the potential energy landscape that they inhabit. And specifically, this paper looks at a system of bosons on a three-dimensional torus.
A torus, like a donut shape.
Precisely. They've confined these bosons to this donut-shaped space, and these bosons interact weakly and are governed by a specific Hamiltonian.
All right.
Now, this Hamiltonian has what we call U1 symmetry.
Okay.
It means that the number of particles in the system stays constant.
Right.
No particles magically appear or disappear.
Right. So that's the fundamental principle of conservation of particle number.
Exactly.
But how does Bose-Einstein condensation, the bosons all piling into the same state, mess with this U1 symmetry? That's the part I'm struggling to wrap my head around.
Well, and that's the crux of the paper.
Okay.
They demonstrate that this macroscopic occupation of a single state, which is like the hallmark of BEC, leads to the breaking of the U1 symmetry.
Interesting.
And they use this clever mathematical tool called quasi-averages,
Okay.
introduced by Bogoliubov, to prove this connection.
Quasi-averages. Can you unpack that a bit for me? It sounds pretty technical.
Yeah, so it's a way to mathematically capture the subtle effects of symmetry breaking.
Okay.
Imagine gently nudging that ball at the top of the hill.
Okay.
Just a tiny perturbation. Quasi-averages let you study what happens as you make that nudge smaller and smaller.
So we're basically introducing like a tiny perturbation into our system of bosons to see if it like rolls down the hill and breaks the symmetry.
Exactly.
Okay.
And the paper rigorously shows that this breaking of the U1 symmetry happens if and only if Bose-Einstein condensation occurs. And their proof relies on deriving precise upper and lower bounds for the grand potential of the system.
Hold on, grand potential. Can you just remind me like what that signifies?
Yeah, so think of it as a thermodynamic function that kind of encapsulates the energy and entropy of the system.
Yeah.
And by analyzing this grand potential,
Mm-hmm.
they gain deep insights into the system's behavior and its propensity for Bose-Einstein condensation.
Okay, got it. So they set out to prove that in this system of weakly interacting bosons on a torus,
Yeah.
Bose-Einstein condensation is like equivalent to breaking the U1 symmetry.
Right.
And they do this by meticulously examining the grand potential.
Yep.
Sounds like a challenging mathematical journey.
It is, but before we dive into like all the details of their proof, let's set the stage.
Okay.
The system that they analyze is what we call a mean field Bose gas.
Okay.
So this means that the interaction between bosons is treated in a specific way that simplifies the analysis but still captures the essential physics.
Right, a kind of like idealized model that makes the calculations easier.
Exactly.
So walk us through their approach. How do they go about proving this equivalence between BEC and U1 symmetry breaking?
They employ a two-pronged strategy.
Okay.
They derive both an upper and a lower bound for the system's grand potential.
Okay.
And this gives them a tight mathematical grip on the system's behavior.
Okay, I'm following so far. Let's start with the upper bound. How do they determine that?
So to get an upper bound, they use a carefully chosen trial state for the system.
Well,
This trial state treats the zero momentum mode, which is the state where all the bosons congregate in BEC, as what we call a coherent state.
a coherent state? Can you elaborate on that a little bit? I've heard the term before.
But think of a laser beam where all the photons are oscillating in perfect unison.
Yeah.
That's the essence of a coherent state. It's a highly ordered, almost classical-like state where the particles are behaving in a synchronized manner.
So they're essentially saying, let's assume the bosons in that zero momentum state are behaving like this well-organized laser beam.
Exactly. And see what happens mathematically. They treat the zero momentum mode as a coherent state while considering the other particles, the ones not part of the condensate, as an ideal gas.
Okay.
And this trial state, with these assumptions baked in, provides a good upper bound for the grand potential.
That's clever. But what about the lower bound? I imagine that's a bit trickier to pin down.
You're absolutely right. The lower bound requires a more intricate approach.
Okay.
They start by establishing a lemma that provides a simple lower bound for the interaction term in the Hamiltonian.
A lemma.
Yeah, it's like a mini theorem,
Oh.
stepping stone to the bigger proof.
Okay.
And they use this lemma to derive a lower bound for the grand potential. But to make this bound as tight as possible, they employ a technique called C-number substitution.
Okay, now we're getting into the heavy machinery of quantum field theory. A little bit.
So C-number substitution, can you give us a glimpse into what that entails? I know it involves replacing quantum operators with ordinary numbers, but how does that actually work in practice?
It's a powerful technique that simplifies the analysis without sacrificing too much accuracy.
Oh, okay.
Essentially, they replace the creation and annihilation operators, which describe the quantum behavior of particles, with ordinary numbers, what we call C numbers.
Okay.
And this simplifies the mathematical expressions while preserving the essential physics of the condensate.
So they're taming the quantum weirdness a bit
A little bit, yeah.
by replacing those unruly operators with some well-behaved numbers.
Right.
But there's more to it, right? You mentioned that they also use entropy to further refine the lower bound.
Yes, they combine C-number substitution with inequalities involving the system's entropy.
Okay.
Entropy, you'll recall, is a measure of disorder or randomness. And by incorporating entropy into their analysis, they squeeze out a tighter, more accurate lower bound for the grand potential. I see. So they're using both the order of the condensate and the disorder of the remaining particles to constrain the grand potential from below.
Yeah, like building a mathematical vice, squeezing it from both sides.
I like that analogy, but I'm eager to get into the details of their proof.
Okay.
They've set the stage in there, established these bounds. Now, how do they connect it all back to the original question of BEC and symmetry breaking?
That's where it gets even more interesting.
All right.
They delve into the intricacies of their effective theory for the condensate,
Okay.
introducing this new variable that represents the square root of the number of particles in the excited states scaled by a factor related to the system size.
Okay, so they're getting deep into the mathematical weeds here.
A little bit, yeah.
Why do they need to introduce this new variable? It seems like they're adding complexity to an already complex problem.
It's all about getting the tightest possible bound on the grand potential. This new variable allows them to carefully examine different cases and regimes of the system, ultimately leading to a more precise and rigorous analysis of the relationship between BEC and symmetry breaking.
Okay.
By minimizing the lower bound expression with respect to this new variable and the absolute value of the condensate wave function, they can really zoom in on the subtle interplay between condensation and symmetry.
Okay, so they've meticulously derived these upper and lower bounds.
Right.
And they've introduced this new variable to make the analysis even more precise. But how do they actually use these results to demonstrate the equivalence between BEC and U1 symmetry breaking?
That's where the magic of the Hellman-Feynman theorem comes in.
Ah, yes.
It's a powerful tool that connects changes in a system's energy to changes in its parameters, and they employ a variant of this theorem known as a first-order Griffith argument
Okay.
to extract crucial information about the condensate fraction and the quasi-averages from the bounds on the grand potential.
The condensate fraction, you mentioned it earlier, but can you remind us what that is and why it's important?
Yeah, so the condensate fraction is simply the proportion of particles that have joined the big party in the zero momentum state.
Okay.
It tells us how much of the system has condensed into that lowest energy state.
Right, so a higher condensate fraction means more bosons are participating in the BEC.
Exactly.
And they use this Griffith argument to link the grand potential which they've painstakingly bounded to the condensate fraction and those quasi-averages we discussed earlier.
Exactly. The Griffith argument allows them to bound the condensate fraction and the quasi-averages in terms of the difference between the grand potential at slightly different values of the perturbation parameter, and because they have such tight bounds on the grand potential, they have excellent control over these differences.
Okay, I'm starting to see the big picture. They've constructed this elaborate mathematical framework, carefully analyzed the grand potential from both above and below. And now they're using this framework to extract precise information about the condensate and its impact on the system's symmetry.
Yes, and by combining the Griffith argument with those tight bounds, they're able to demonstrate a crucial result in the limit of large system size. The condensate fraction is non-zero if and only if the U1 symmetry is broken as measured by those quasi-averages. This rigorously establishes the equivalence between BEC and spontaneous symmetry breaking in this system.
This is seriously impressive work.
It is.
They've combined deep physical intuition with some sophisticated mathematical techniques.
Yeah.
To unravel the connection between these two fundamental phenomena, it's mind-blowing to see how seemingly abstract concepts like symmetry breaking have such tangible consequences in the physical world.
It's a testament to the power of theoretical physics, but we're just getting started. Their paper goes even deeper, exploring the properties of the effective chemical potential and delving into the proof of their main theorem, which connects all the pieces of the puzzle.
I'm hooked. Let's take a closer look at that effective chemical potential and see what insights they've uncovered.
Okay. So we've seen how Deutschert-Nahm and Napierkowski established this remarkable connection between Bose-Einstein condensation and the breaking of the U1 symmetry. But their exploration doesn't stop there. They delve deeper into the system's behavior, focusing on a quantity known as the effective chemical potential.
Okay, the effective chemical potential. You've mentioned it a few times, but to be honest, I'm still a bit fuzzy on what it represents and why it's so important in this context. Can we unpack that a bit?
Of course, the effective chemical potential, often denoted as Mestel, is a key player in understanding the energetics of the system. It captures the interplay between the interaction strength among the bosons, the temperature, and the system's chemical potential.
So it's like a behind-the-scenes director orchestrating how the bosons distribute themselves among the energy levels.
Exactly. It influences whether the bosons prefer to join the party in the zero momentum state, forming the condensate, or hang out in higher energy states.
Okay, that makes sense. So what have they discovered about this effective chemical potential? What secrets does it hold about the system's behavior?
They've uncovered 3 key properties of mu tilde, all related to how it behaves as the system size increases, which we represent with the parameter eta.
Okay, so as our donut-shaped space gets bigger and bigger, how does this mu tilde change?
First, they prove that for any given temperature interaction strength and chemical potential, there's only one unique solution for mu tilde. This is important because it means mu tilde is well-defined. There's no ambiguity about its value.
So no quantum identity crisis for mu tilde, just one clear and consistent value. What about the other properties?
The second property they demonstrate is that mu tilde is always less than or equal to 0. This is physically significant because it means the effective chemical potential is always lower than the energy of the zero momentum state, the ground state.
I see. So it's like mu tilde is offering an energetic incentive for the bosons to stay out of the condensate to explore higher energy levels.
That's a great way to think about it. Now, the third property, it's a bit more intricate. They consider a specific scaling regime where the inverse temperature, denoted by beta scales with the system size as eta to the power of minus 2/3. At the same time, the chemical potential mu is bounded between minus eta to the power of 2/3 and some constant value.
Hold on, why this specific scaling? It seems a bit arbitrary.
It's not arbitrary at all. It corresponds to a regime where the system can exhibit both condensed and non-condensed phases. Remember, Bose-Einstein condensation is a phase transition, and the scaling allows them to study how the system behaves near the critical temperature where that transition occurs.
Okay, so it's a way to zoom in on the transition point where the bosons are on the verge of condensing.
Precisely. And in this regime, they find that the difference between the actual chemical potential mu and the effective chemical potential mu tilde remains bounded within a certain range in simpler terms. Even though mu tilde is always less than or equal to 0, it doesn't stray too far from mu.
So even though mu tilde is enticing bosons to explore higher energy levels, it's still keeping an eye on the actual chemical potential mu. It's like a loyal sidekick, always staying close, but maintaining a bit of independence.
That's a great analogy. They further refine this result by considering two cases, one where the chemical potential is positive and another where it's negative. When mu is positive, they show that minus mu tilde is bounded by a constant.
So in this case, when there's a surplus of particles eager to join the condensate, mu tilde stays relatively well behaved within a limited range.
Exactly. But when mu is negative, the situation changes. They find that minus mu tilde can become quite large scaling with the system size as eta to the power of 2/3.
So when the chemical potential is negative, mu tilde becomes a bit wilder, exerting a stronger influence to keep bosons out of the condensate.
Precisely. And this difference in behavior makes physical sense. When mu is positive, there's already a strong drive for bosons to condense, so tilde doesn't need to do much, but when mu is negative, it's like trying to convince introverted particles to join a party. You need a stronger incentive, a lower mu tilde to coax them out of their ground state comfort zone.
This is starting to paint a really clear picture of how mu tilde plays a crucial role in this delicate dance between condensation and the system's energy landscape. But you mentioned they also explored a specific sum involving mu tilde. What's the story there?
Yes, they analyze a sum that appears in the calculation of the grand potential. This sum involves terms that depend on the momentum of the particles and the effective chemical potential. Mu tilde, they rigorously prove that this sum is proportional to eta, the system size.
Okay, so this sum, which captures some aspect of the system's energy scales linearly with the size of our donut-shaped space. Why is that finding significant?
It has important consequences for understanding the thermodynamic properties of the system as it grows larger. It tells us how the energy and entropy of the system scale with its size, which is crucial for understanding phase transitions like BEC.
Okay, I'm with you. So we have these three key properties of mu tilde. A unique solution always less than or equal to 0, and scaling differently depending on the chemical potential. Plus, we have this sum involving mu tilde that's proportional to the system size. But how do they actually prove all of this? What kind of mathematical wizardry are they employing?
Their proofs involve a combination of clever analytical techniques. They start by defining a function of mu tilde, which essentially rearranges the equation that defines mu tilde. This function has some very helpful properties. It's continuous, strictly increasing, and its limits at negative and positive infinity are well defined.
So it's a well-behaved function that encapsulates the essence of mu tilde.
Exactly, and because of these nice properties, they can use standard calculus arguments to prove that a unique solution for mu tilde exists. They then use a series of inequalities, including a crucial one involving the exponential function, to derive those bounds on the difference between mu and mu tilde.
I see they're leveraging the tools of calculus to tame these abstract quantities.
Precisely. And they don't stop there to handle those infinite sums that pop up in the analysis of the mean field Bose gas. They employ a powerful lemma that lets them approximate these sums with integrals.
So they're bringing in the big guns of mathematical analysis. They're really pulling out all the stops to understand this system.
They meticulously manipulate the equations, strategically apply inequalities, and employ powerful approximation techniques to uncover those essential properties of mu tilde. It's a testament to the rigor and beauty of theoretical physics.
This deep dive is truly living up to its name. It's amazing to see how they've combined deep physical intuition with this sophisticated mathematical framework to reveal the secrets of mu tilde and its role in BEC. But I know there's more to the story. They don't just stop with these properties, right? They go on to prove a central theorem that connects all the pieces we've been discussing.
You're absolutely right. The culmination of their work lies in the proof of Theorem 1.1, which brings together BEC-U1 symmetry, breaking the condensate fraction and those quasi-averages into one grand unified statement.
Okay, I'm on the edge of my seat. Let's delve into that theorem and see what insights it reveals. All right, so we've explored spontaneous symmetry breaking, we've unpacked the mysteries of the effective chemical potential, and now we're ready to tackle the heart of this paper, Theorem 1.1. It sounds like this is where all the pieces of the puzzle come together.
You're exactly right. Theorem 1.1 is a culmination of all their meticulous analysis, a mathematical tour de force that connects Bose-Einstein condensation U1 symmetry, breaking the condensate fraction, and those quasi-averages we've been discussing.
Okay, I'm ready for the grand finale. Break it down for me. What are the key takeaways of this theorem? What insights does it offer?
So Theorem 1.1 is divided into three parts, each providing a crucial piece of the puzzle.
Right.
Part A establishes that the system undergoes a genuine Bose-Einstein condensation phase transition. It shows that as the system size grows, the condensate fraction, the proportion of particles in the zero momentum state, approaches a specific value.
So part A confirms that BEC actually happens in this system. Does it tell us anything about the value that the condensate fraction approaches?
It does. It provides a precise formula for this value, and it depends on the ratio between the inverse temperature and a critical inverse temperature. This critical temperature is defined in terms of the chemical potential, the interaction strength, and a mathematical constant known as the Riemann zeta function.
Okay, so part A nails down the BEC phase transition and gives us a formula for the condensate fraction. What about part B? What does that reveal?
Part B is the real showstopper. It rigorously proves that the U1 symmetry of the system is broken if and only if the system exhibits Bose-Einstein condensation. This is the mathematical confirmation of that intuitive idea we discussed earlier. The crowding of bosons into the zero momentum state leads to the breaking of the symmetry associated with particle number conservation.
Wow, that's a profound connection.
Yeah.
They've mathematically demonstrated that these two phenomena, BEC and U1 symmetry breaking, are like inextricably linked in this system.
Yeah.
But how do they actually show that? What's the logic behind their proof?
They demonstrate that the quasi-averages, which we've discussed as those mathematical quantities designed to detect symmetry breaking, have a non-zero limit if and only if the system displays BEC. It's a powerful equivalence connecting a thermodynamic phenomenon BEC with a fundamental symmetry principle.
Okay, so part B solidifies the connection between BEC and symmetry breaking. What's the final piece part? See, what does that add to the picture?
Part C zooms in on the condensate fraction in the perturbed system, where we've introduced those tiny perturbations to probe the system's response. It shows that as the system size increases, the condensate fraction in the perturbed system approaches the same value as in the unperturbed system.
So those tiny perturbations we introduced to test the system don't fundamentally alter the amount of condensation that occurs.
Exactly. The condensate fraction remains robust, insensitive to small perturbations. This further solidifies its role as a key indicator of BEC, a quantity that captures the essence of this phase transition.
This theorem is truly remarkable. It's like a grand unified theory of BEC and symmetry breaking in this system. But I have to ask, how do they actually prove all of this? I can only imagine the mathematical acrobatics involved.
You're right, the proof is quite intricate, but we can sketch out the main ideas for part A. They cleverly employ another Hellman-Feynman type argument, this time focusing on the unperturbed grand potential. By differentiating this grand potential with respect to a parameter that controls the occupation of a specific momentum state, they can extract information about the condensate fraction.
So they're using the grand potential as a mathematical tool to probe the condensate's behavior.
Precisely. And by carefully analyzing the bounds they derived for the grand potential earlier, they can show that the condensate fraction approaches the expected value as the system size grows, confirming the BEC phase transition.
Okay, that makes sense. What about part B, the equivalence between BEC and symmetry breaking? How do they tackle that proof?
For part B, they use a similar strategy, but this time they differentiate the perturbed grand potential with respect to the parameter lambda, which controls the strength of that symmetry-breaking perturbation.
So they're tweaking the perturbation and seeing how the grand potential responds.
Exactly. By analyzing this derivative, they can connect the quasi-averages, which signal symmetry breaking, to the difference in the grand potential at slightly different values of lambda. Again, those tight bounds they derive for the grand potential play a crucial role here, giving them precise control over these differences and allowing them to prove the equivalence.
Okay, I'm following the logic. And what about part C, the robustness of the condensate fraction? What's the key to proving that?
For part C, they combine the results from parts A and B with a clever argument involving the Cauchy-Schwarz inequality. This inequality, a fundamental tool in mathematics, lets them relate the absolute value of the condensate wave function to the condensate fraction, ultimately proving that the condensate fraction remains stable even at zero perturbation.
This is some seriously impressive mathematical work. They have woven together a tapestry of sophisticated techniques to prove this beautiful theorem. But stepping back for a moment, why should our listeners care about all of this? What's the big picture significance of BEC and spontaneous symmetry breaking?
This paper is a shining example of how deep mathematical concepts can illuminate our understanding of the physical world. BEC and spontaneous symmetry breaking aren't just abstract theoretical ideas. They have profound implications for a wide range of physical systems, from superfluids and superconductors to cosmology and particle physics.
I see. So understanding these phenomena in this relatively simple model system can provide insights into much more complex and diverse areas of physics.
Exactly. By rigorously proving the equivalence between BEC and U1 symmetry breaking in this mean field Bose gas, the authors have provided a powerful tool for understanding these phenomena in other contexts.
This has been a truly enlightening deep dive. We've journeyed into the world of Bose-Einstein condensation, explored the subtleties of symmetry breaking, and witnessed the power of rigorous mathematical analysis.
And it's a reminder that even in the seemingly chaotic world of quantum mechanics, there's a deep underlying order governed by fundamental symmetries.
A huge thank you to our listeners for joining us on this incredible journey into the quantum realm. We encourage you to explore the source material yourselves and continue to marvel at the wonders of physics. Until next time, keep those minds curious and those questions coming. Welcome to the deep dive. Today we're diving into quantum physics.
Okay.
Specifically, a phenomenon called spontaneous symmetry breaking.
Okay.
In a system of interacting bosons.
Right.
It blends like these really abstract mathematical concepts with some profound physical implications.
Yeah.
And you've provided us with a paper called A Note on Spontaneous Symmetry Breaking in the Mean Field Bose Gas.
Great.
Which looks into this very topic.
Yes.
And we have our mathematical physics expert here to help us unpack it all.
I'm thrilled to be here. Yeah, this paper is a fascinating deep dive into the intersection of quantum mechanics and statistical mechanics.
Right.
And it's packed with intricate mathematical arguments.
Okay, so let's set the stage.
Sure.
This paper focuses on a system of bosons.
Okay.
And it explores a specific type of symmetry breaking.
Right.
Known as U1 symmetry breaking.
Yep.
Could you give us a primer on what spontaneous symmetry breaking means in this context?
Absolutely. In simple terms, spontaneous symmetry breaking occurs when the ground state, or the lowest energy state of a system, doesn't possess the same symmetries as the laws governing the system.
Okay.
Think of a ferromagnet.
Right.
The laws of physics that govern the spins in a ferromagnet are rotationally symmetric.
Okay.
However,
yeah.
Below a certain critical temperature, the spins align in a specific direction, breaking that rotational symmetry.
So I'm picturing like a perfectly round ball at the top of a hill.
Okay.
Like the ball and the hill are perfectly symmetrical, but if the ball rolls down, it has to choose a direction.
Exactly.
Breaking that initial symmetry.
That's a great analogy.
Okay.
In our quantum system, the U1 symmetry is related to the conservation of particle number.
Right.
The laws of quantum mechanics dictate that in a closed system, the total number of particles should remain constant. However, when spontaneous symmetry breaking occurs, the system behaves as if the symmetry is broken.
So it's not that the number of particles actually changes.
Right.
But rather that the system's behavior doesn't reflect that conservation law in the ground state.
Precisely. What changes is the distribution of particles among different energy levels.
Okay.
And this brings us to a fascinating connection that the paper explores.
Right.
The link between spontaneous U1 symmetry breaking and Bose-Einstein condensation, or BEC.
BEC. The phenomenon where a bunch of bosons decide to hang out in the lowest energy state, forming a sort of quantum superatom.
Exactly.
I remember learning about it in college, but it's always felt a bit magical to me.
It is a remarkable phenomenon.
Yeah.
And as this paper elegantly demonstrates, there's a deep mathematical connection between BEC and the breaking of U1 symmetry. They show that in the system they're studying, these two phenomena are essentially two sides of the same coin.
That's a bold claim.
It is.
So to dive into the specifics, this paper focuses on a system of interacting bosons confined to a three-dimensional flat torus.
Right.
For our listeners who might not be familiar with this, could you paint a picture of what that looks like?
Imagine a cube where if you travel out of one side, you re-emerge on the opposite side. It's essentially a mathematical model for a space with periodic boundary conditions. In this space, we have a collection of bosons that are interacting with each other. And the paper explores how those interactions combined with the system's geometry lead to the emergence of BEC and spontaneous symmetry breaking.
I'm visualizing this torus filled with interacting bosons.
Right.
Now, to understand how the paper tackles this problem mathematically, we need to delve into the language they use.
Sure.
They start by describing the system using the bosonic Fock space.
Right.
And a specific Hamiltonian.
Okay.
Could you break down these concepts for us?
Certainly. The bosonic Fock space is a mathematical framework that allows us to represent systems with a variable number of particles.
Okay.
It's essentially a direct sum of Hilbert spaces, where each space corresponds to a specific number of particles.
So it's like a giant container that can hold any number of particles,
Exactly.
and each section of the container represents a different particle number.
Exactly.
Cool.
And the Hamiltonian, represented by H,
Okay.
is an operator that describes the total energy of the system.
All right.
In this case, the Hamiltonian is composed of a kinetic energy term,
Okay.
represented by the Laplacian operator,
Ah.
and an interaction energy term, denoted by V.
So the Hamiltonian's like a recipe for the system's energy.
Yes.
With ingredients for both the movement of the particles
Yeah.
and their interactions with each other.
A very insightful analogy.
Okay.
The Hamiltonian captures the dynamics of the system,
Okay.
how the particles move and interact over time,
Got it.
and to make things even more interesting, the paper introduces something called mean field scaling.
Mean field scaling. Does that imply that all the bosons are just going with the flow?
Well,
Like sheep in a field?
that's a fun way to think about it,
Okay.
though not entirely accurate.
Right.
Mean field scaling is a way of describing the strength of the interactions between the bosons in this scaling.
Yeah.
The interaction strength is inversely proportional to the number of particles.
Okay.
As the number of bosons increases,
Mm-hmm.
the individual interactions become weaker.
So it's like a crowded party.
Yeah.
The more people there are,
Yeah.
the less likely you are to have a deep conversation with any one person.
Right.
You're just interacting with the crowd as a whole.
Exactly.
Okay.
And this mean field approximation simplifies the problem significantly,
Okay.
allowing us to analyze the system's behavior using powerful tools from statistical mechanics.
This brings us to another concept the paper mentions,
Right.
the grand canonical ensemble.
Yeah.
Could you explain what that is and why it's relevant here?
The grand canonical ensemble is a powerful framework in statistical mechanics that allows us to describe systems that can exchange both energy and particles with their surroundings.
Okay.
It's particularly useful when dealing with systems where the number of particles isn't fixed,
Okay.
like in the case of BEC.
So instead of us assuming a fixed number of bosons,
Exactly.
we're allowing for the possibility of particles coming and going,
Right.
which seems appropriate given that we're dealing with a condensate that can grow or shrink.
Exactly.
Okay.
And the grand canonical ensemble uses two key parameters,
Right.
the inverse temperature, denoted by BOP,
Mm.
and the chemical potential represented by.
Okay. Remind me what the chemical potential represents again.
The chemical potential is essentially a measure of how much the system's energy changes when you add or remove a particle,
Okay.
keeping other parameters like temperature and volume constant.
So it tells us how eager the system is to accept a new particle
Precisely.
or to let one go.
Yeah.
A higher chemical potential means the system is more welcoming to new particles.
Precisely.
Okay.
And these two parameters, organ, play a crucial role in determining the equilibrium state of the system, which is known as the Gibbs state.
Gibbs state sounds like a very relaxed state of being.
In a way, yes.
Oh.
The Gibbs state represents the most probable state of the system at a given temperature and chemical potential.
Mm-hmm.
It's like a snapshot of the system when it has settled down and reached a state of thermodynamic equilibrium.
Got it. So we've established the basic setting.
Right.
We have a system of interacting bosons in a 3D torus,
Right.
described using the bosonic Fock space,
Yep.
and a Hamiltonian with mean field scaling.
Uh-huh.
We're also considering the system within the framework of the grand canonical ensemble,
Right.
using temperature and chemical potential to define the Gibbs state.
Okay.
What comes next?
Well, the paper claims that spontaneous U1 symmetry breaking happens in this system of interacting bosons,
Oh,
if and only if the system exhibits BEC, and they set out to rigorously prove this claim.
that's a fascinating claim.
It is.
And how do they go about proving this?
The proof involves several intricate steps.
Okay.
They use the Gibbs variational principle to analyze the grand potential of the system.
Right.
This grand potential, often denoted by A,
Mm-hmm.
is a thermodynamic quantity
Right.
that plays a crucial role in determining the equilibrium state.
Okay.
The state that minimizes the grand potential is the equilibrium state.
So it's like finding the lowest point in an energy landscape.
Exactly.
The system naturally wants to settle into this state with the lowest grand potential.
Exactly.
Okay.
And to study the connection between BEC and symmetry breaking,
Mm-hmm.
they introduce perturbations to the system.
Perturbations,
Yeah.
like giving the system a little poke to see how it reacts.
Yes.
Okay.
They consider two types of perturbations.
Okay.
The first one explicitly breaks the U1 symmetry,
Okay.
represented by a term in the Hamiltonia,
Right.
proportional to lambda. multiplied by the sum of the creation and annihilation operators for the zero momentum state.
So they're deliberately messing with the particle number conservation.
Precisely.
In a controlled way.
Precisely.
Okay.
The second perturbation is of the form, arrow, which essentially modifies the energy of the zero momentum state.
Okay, so they're tweaking the system in two specific ways.
Exactly.
One targeting the symmetry directly.
Right.
And the other influencing the energy of the ground state.
Exactly.
Okay.
Next, they derive upper and lower bounds for the perturbed grand potential.
Okay.
This involves a lot of mathematical heavy lifting,
right?
Using techniques like trial states, Onsager's lemma, and the C-number substitution.
Oh, those are some fancy mathematical terms?
They are.
Can we break those down a bit?
Sure.
What are trial states, for example?
Trial states are essentially educated guesses for the system state.
Okay.
They are cleverly chosen to make calculations easier and to obtain bounds on the grand potential.
Got it.
It's like saying, we don't know the exact solution, but we're pretty sure it lies somewhere within this range.
Okay, so it's a way to narrow down the possibilities.
Exactly.
And what about Onsager's lemma?
Onsager's lemma is a powerful tool that allows us to relate the properties of an interacting system to those of a non-interacting system.
Right.
It's incredibly useful for simplifying calculations in statistical mechanics.
So it helps bridge the gap between the simple world of non-interacting particles and the more complex world of interacting ones.
Precisely.
Okay.
And finally, the C-number substitution allows us to treat certain quantum operators as if they were classical numbers.
Okay.
This is particularly helpful when dealing with Bose-Einstein condensates, where a macroscopic number of particles occupy the same quantum state.
So it's a way to simplify the math without losing the essence of the quantum behavior.
Exactly.
Okay.
And these techniques help them to analyze the grand potential and connect it to both BEC and symmetry breaking.
This has been a fantastic overview of the setup and the tools involved.
Right.
I'm eager to dive into the details of the proof itself and see how they actually demonstrate this equivalence.
Right.
It's amazing how these seemingly abstract mathematical tools can unravel such profound physical connections.
It is.
Okay, we've set the stage and explored the mathematical toolbox.
Right.
Now let's dive into the heart of the paper.
All right.
The proof itself.
Great.
So they use a clever tool called the Griffith argument, also known as the Hellman-Feynman theorem.
Right.
Can you illuminate this for me?
Absolutely.
Okay.
The Griffith argument is a powerful technique that allows us to extract information about a system by analyzing how its energy changes in response to a perturbation.
Okay.
Imagine you have a delicate system in equilibrium, and you gently nudge it by observing how the system responds to that nudge.
Okay.
You can learn about its internal structure.
So it's like poking a sleeping bear.
Precisely.
In a very gentle and mathematical way.
Exactly. Okay. Except in this case, our bear is the grand potential.
Okay.
And our poke is the introduction of those perturbations we discussed earlier. By analyzing how the grand potential changes with respect to the perturbation parameters, lambda and delta, we can gain insights into the system's behavior.
Okay. I'm following so far.
All right.
We're using these perturbations as probes to tickle the grand potential and see how it wiggles.
Exactly.
But how does this help us prove the equivalence between BEC and symmetry breaking?
Remember those upper and lower bounds? For the perturbed grand potential we talked about? Those bounds are crucial here. By applying the Griffith argument, we can translate those bounds into statements about the system's behavior as the perturbations are switched on or off.
So those bounds are not just mathematical curiosity.
Right.
They provide a framework for understanding how the system responds to these perturbations.
Exactly.
And ultimately how those responses relate to BEC and symmetry breaking.
Exactly. The Griffith argument essentially allows us to connect the dots between the behavior of the grand potential under perturbation and the physical phenomena of BEC and symmetry breaking.
Okay, I'm ready to walk through the proof.
Sure.
What are the key steps involved in applying this Griffith argument?
The first step is to differentiate the perturbed grand potential with respect to each of the perturbation parameters, lambda and delta. This gives us expressions that involve the expectation values of certain operators, such as the creation and annihilation operators for the zero momentum state, noted by AAO and EAO.
So we're essentially looking at how the grand potential slope changes.
Exactly.
As we tweak the strength of the perturbations.
Yes.
And those slopes are related to the behavior of these quantum operators. operators, which govern the creation and annihilation of particles in the ground state.
Precisely.
Okay.
Now a crucial property comes into play.
Right.
The grand potential is a concave function.
Okay.
This means that any line segment connecting 2 points on the curve of the grand potential lies below the curve itself.
Concavity. I vaguely remember that from calculus class.
Yes.
It means the function curves downward like a frowning face.
Exactly.
Right.
And this concavity property is key to the Griffith argument.
Okay.
It allows us to use those derivatives we just calculated to establish upper and lower bounds on the expectation values of those operators.
Okay.
We can essentially sandwich those expectation values between two well-defined mathematical expressions.
Fascinating. So concavity acts like a mathematical vice,
That's a great way to visualize it.
squeezing those expectation values between two limits determined by the behavior of the grand potential under perturbation.
Now, here's where things get a bit subtle.
Okay.
The Griffith argument, when applied to the lambda perturbation, initially gives us bounds on the expectation value of the sum of the creation and annihilation operators for the zero momentum state, not the individual operators themselves.
Why the sum? Why not look at them individually right from the start?
That's because the symmetry breaking perturbation we introduce
Right.
is proportional to the sum of those two operators.
Okay.
To analyze the effect of that specific perturbation, we need to focus on their combined behavior.
That makes sense.
Okay.
But to demonstrate symmetry breaking,
Right.
we ultimately want to show that the expectation value of the annihilation operator itself
Yes.
becomes non-zero in the condensed phase.
Precisely.
That's the hallmark of a broken symmetry.
You're absolutely right.
Okay.
So we need an extra step to go from the bounds on the sum to bounds on the individual annihilation operator.
Okay, how do we bridge that gap?
Here we combine the bounds from the Griffith argument with another result. The paper establishes the behavior of the condensate fraction in the perturbed system.
Okay.
The paper demonstrates that the condensate fraction, which is essentially the expectation value of the number operator for the zero momentum state, AA, approaches a non-zero value in the condensed phase.
Right. That was a key part of showing that BC actually occurs in this system.
Exactly.
We see this macroscopic occupation of the ground state.
Exactly. Now we have these three pieces of information.
Okay.
The bounds on the sum of the creation and annihilation operators from the Griffith argument, the knowledge that the condensate fraction becomes non-zero in the condensed phase, and the relationship between these quantities and the expectation value of the annihilation operator itself.
So it's like solving a mathematical jigsaw puzzle.
Precisely.
We have these different pieces.
Yeah.
And by carefully fitting them together, we can reveal the full picture. The behavior of the annihilation operator and the emergence of symmetry breaking.
Precisely. And by meticulously analyzing these relationships, the authors demonstrate that the expectation value of the annihilation operator indeed becomes non-zero in the condensed phase. This is the smoking gun, the mathematical signature of a broken U1 symmetry.
Wow. So they've managed to rigorously connect the dots between the behavior of the grand potential under perturbation and the emergence both BEC and symmetry breaking.
Yes.
It's incredible how these abstract mathematical tools can unveil such profound physical connections.
It truly is a testament to the power of mathematical physics. And this is just the first part of their proof. They go on to demonstrate the converse. If the U1 symmetry is broken, then the system must exhibit BEC. This involves a slightly different application of the Griffith argument, focusing on the derivative of the grand potential with respect to the delta perturbation.
So they're essentially going in the reverse direction now.
Exactly.
Showing that symmetry breaking implies BEC. They're building a two-way street between these two phenomena.
Exactly. And by establishing both directions of this connection, they solidify their main result. The equivalence between BEC and spontaneous U1 symmetry breaking in this mean field Bose gas.
This has been an incredibly insightful journey through the mathematical intricacies of the proof. It's amazing how much we can learn about the physical world through the lens of these powerful mathematical techniques.
It is.
So we've unpacked the proof showing the equivalence of BEC and U1 symmetry breaking in this system. But the paper doesn't stop there.
No, it doesn't.
It delves into this fascinating concept of a self-consistent ideal gas. Feels like a bit of a contradiction.
It does.
How can a gas be both ideal and self-consistent,
Right.
especially when we're dealing with interactions.
Well, it's a clever theoretical tool, a way of simplifying the complexities of the interacting system.
Right.
Imagine you have all these bosons bouncing off each other.
Okay.
Instead of tracking every single interaction,
Yeah.
we replace them with an average effect. This average effect is incorporated into a modified chemical potential.
So we smooth out the interaction
Exactly.
and treat the bosons as if they're essentially non-interacting,
Right.
but with this tweaked chemical potential that captures the average behavior of the system.
Precisely.
Okay.
This simplification lets us use the well-understood mathematics of the ideal Bose gas to analyze the more complex interacting system.
Okay.
It's a brilliant bridge between a familiar territory and the uncharted world of interacting bosons.
This self-consistent ideal gas framework seems crucial for determining the critical temperature for BEC in the interacting model, isn't it?
Absolutely.
Okay.
By analyzing this self-consistent ideal gas, the authors define a critical temperature denoted as both below which we expect BEC to occur in the interacting system.
Right.
This BAC depends on the interaction potential and the chemical potential.
So we have a formula then that tells us at what temperature this transition to a Bose-Einstein condensate will happen.
Exactly.
Even with interactions considered.
Right.
Is there anything surprising about this critical temperature?
There is.
Okay, what is it?
The paper shows that as the interaction strength increases, this critical temperature also increases.
Okay.
Stronger interactions lead to a higher critical temperature for BEC.
That's counterintuitive.
It is.
Wouldn't stronger interactions make it harder for the bosons to condense?
You would think so.
Not easier.
Right.
I imagine them bouncing around more.
Yeah.
Resisting settling into that lowest energy state.
That's a reasonable assumption.
Yeah.
But remember, we're working within the mean field approximation.
Okay.
The interactions are diluted as the number of particles grows.
So the strength of individual interactions isn't the deciding factor, but rather the overall average effect of these interactions.
Exactly.
Across the entire system.
Exactly. In this mean field scenario, the interactions actually act as a stabilizing force.
Okay.
Encouraging the bosons to condense.
It's like those interactions, while seemingly disruptive, are actually helping hold the condensate together.
That's a great way to put it.
Okay.
This paper underscores how emergent phenomena arise from the complex interplay of many individual components.
This has been a phenomenal deep dive.
It has.
We've journeyed through spontaneous symmetry breaking, Bose-Einstein condensation, the concept of a self-consistent ideal gas, the surprising role of interactions, and the rigorous mathematical proofs that underpin it all.
Absolutely.
And though the mathematics might seem daunting, remember the key takeaway.
Okay.
Even in the quantum realm, where uncertainty reigns, there's an underlying order, a symphony of interactions and symmetries orchestrating the behavior of matter.
Very well said.
For our listeners, if you're ready to tackle the mathematical details, the full paper is linked in our show notes.
Great.
Until next time, keep diving. All right, so welcome to the deep dive. Today, we're going to take a deep dive into some research that you sent our way, a paper titled A Note on Spontaneous Symmetry Breaking in the Mean Field Bose Gas.
Oh, wow. Classic.
Yeah, so buckle up, everyone. We're going to explore the world of bosons, symmetry breaking, and Bose-Einstein condensation.
Yes. This paper is, well, it's quite a ride. Ducher, Nahm, and Napiorkowski really, they really went deep on this one. They're exploring how spontaneous symmetry breaking happens within a system of interacting bosons. It gets pretty complex, but that's why we're here. We're going to try to break it down for you.
Absolutely. So to set the stage, we are dealing with a system of bosons, those particles that love to bunch up in the same quantum state.
Yes.
And this paper dives into the nitty-gritty of how this bunching is known as Bose-Einstein condensation, or BEC for short, and how it's linked to something called spontaneous symmetry breaking.
It's a bit like, imagine a perfectly symmetrical pencil balanced on its tip.
Okay.
The slightest nudge. Yeah.
And it falls, breaking the symmetry.
Right.
In the quantum world, things are a bit more abstract, but the principle is similar. A system can choose a state that doesn't reflect the full symmetry of the laws governing it.
And that's where the mean field Bose gas comes in.
Precisely. The mean field aspect, it simplifies the interactions between the bosons, allowing us to focus on that connection on the BEC and symmetry breaking connection without getting lost in, overly complex calculations.
Okay. So we've got our system of interacting bosons in this mean field scenario.
Yeah.
And the authors are looking at the system on a three-dimensional torus. Why a torus? Is it just to make the math more interesting?
Well, the torus, that donut shape.
Yeah.
It's a common choice in theoretical physics, simplifies the boundary conditions while still capturing, the essential features of a three-dimensional system. Plus, it does make things a bit more visually appealing, don't you think?
Absolutely. Now let's talk about the Hamiltonian.
They used to describe the energy of this system. They include the kinetic energy of the bosons, the weak interaction between them, and then this interesting perturbation term, which is key to their quasi-average approach. Can you unpack that a little?
Of course. The Hamiltonian is essentially the energy operator for the system, and it dictates how the system evolves in time. They include, the usual suspects, the kinetic energy, which represents the particle's motion, and then the interaction term, which describes how the bosons interact with each other.
Right, standard stuff.
Yeah.
But then they throw in this perturbation term. What's the purpose of that?
The perturbation term is, well, it's crucial for their analysis. Remember the analogy of the pencil?
Yeah.
The perturbation is like that gentle nudge, the force that induces the symmetry breaking. By adding this term to the Hamiltonian, they can carefully control and study how the system responds to a force that favors certain states over others.
Okay, I'm starting to see the strategy here. They set up this system, they nudge it a bit, and then they observe how it reacts.
Exactly.
That's where the quasi-averages come in.
Quasi-averages are a way to quantify the effects of this gentle nudge. Instead of abruptly breaking the symmetry, they apply a small perturbation and then calculate the average values of certain quantities, like the creation operator, in the presence of this perturbation.
So quasi-averages are a way to gently probe the system's response to symmetry breaking without completely disrupting its initial state.
Precisely. It's a subtle but powerful technique, and it's key to their main result, which they present in Theorem 1.1.
Right.
This theorem establishes a deep connection between BEC and U1 symmetry breaking in this mean field Bose gas.
Before we get to that theorem, though, can we talk about Proposition 1.1? It seems to set the stage for their main result.
Absolutely. Proposition 1.1 is about the expected number of particles in the system, and they find that this expected number, it grows proportionally to a parameter they denote by eta, it's a Greek letter, A, which controls the strength of the interaction between the bosons.
So the more strongly the particles interact, the more particles we expect to find in this system.
Right.
That makes intuitive sense. But how do they actually prove this? It seems like a pretty fundamental result.
The proof relies on finding upper and lower bounds for the grand potential. Which is a thermodynamic function that, well, it encapsulates the system's energy, including the energy associated with its interaction with a reservoir.
Hold on. Can we pause for a second? For our listeners who might not be as familiar with the grand potential, can you give us a quick refresher on what it represents?
Of course. The grand potential, often denoted by omega, a Greek letter, A, it's a powerful concept in statistical mechanics. It describes the system's ability to exchange both energy and particles with a reservoir. It takes into account the internal energy of the system, the work done by the system, and the energy associated with particle exchange.
Okay, so the grand potential tells us about the system's overall energy in a situation where both energy and particles can be exchanged with the surroundings.
Yes.
And the authors use this concept to prove Proposition 1.1.
Exactly. They establish upper and lower bounds for the grand potential to kind of trap its true value. For the upper bound, they use a clever trial state. They treat the zero momentum mode, where the condensate forms as a coherent state.
A coherent state.
A coherent state is a special quantum state that describes a collection of bosons all occupying the same state. Think of it like a laser beam where all the photons are in the same state.
Okay.
It's a perfect representation of the condensate, where all the bosons are bunched up in the ground state.
Okay, so they represent the condensate using a coherent state. Right? What about the rest of the particles? Those not in the condensate?
For those, they use the Gibbs state of an ideal gas at a specific temperature and chemical potential. Essentially, they're separating the condensate from what we call the thermal cloud of excited particles.
So their trial state is this interesting combination of a coherent state for the condensate and an ideal gas state for the excited particles.
Yes.
And they use this to find An upper bound for the grand potential.
Precisely. They plug this trial state into the formula for the grand potential and calculate an upper limit on the system's overall energy. Then for the lower bound, they utilize a handy tool called Onsager's lemma.
Onsager's lemma.
Onsager's lemma, it provides an inequality
Okay.
that relates the interaction energy of the bosons to the total number of particles. It essentially sets a floor on how low the system's energy can go.
I see. So they've got these upper and lower bounds for the grand potential. How does that help them prove proposition 1.1?
By comparing these bounds, they derive an expression for the expected number of particles in terms of eta, the interaction strength.
Okay.
This expression shows that the expected number of particles grows proportionally to eta, confirming that the model behaves as we'd expect for a mean field system.
Okay, that's pretty neat. They've essentially squeezed the grand potential between these two bounds and extracted valuable information about the system's behavior. Now I think we're ready to tackle the main event, Theorem 1.1.
Absolutely. Let's dive into that. This theorem is where things get really exciting.
Bring it on. I know our listeners are ready to explore the depths of this connection between BEC and symmetry breaking.
All right. So Theorem 1.1 has three key parts.
Okay.
Part A deals with the unperturbed system, meaning the system without the symmetry breaking nudge.
Right.
It states that this system undergoes a BEC phase transition at a specific critical temperature.
So even without any external influence, this system inherently exhibits BEC.
Yes, it's a fundamental property of the mean field Bose gas. Now, Part B is where the connection to symmetry breaking becomes crystal clear. It states that the quasi-average of the creation operator, which is a measure of symmetry breaking, is non-zero precisely when BEC occurs.
Hold on. That's a pretty big deal, right? It means that in this system, BEC and U1 symmetry breaking are essentially two sides of the same coin.
Exactly. It's a stunning connection that goes beyond just observing these phenomena together. It establishes a deep mathematical link between them.
Wow.
And finally, Part C states that the condensate fraction behaves continuously as the perturbation is removed.
So as they dial down the symmetry breaking nudge, the condensate fraction smoothly adjusts without any sudden jumps.
Exactly. It shows the stability of the system and how gracefully it transitions between different states.
Okay, so Theorem 1.1 lays out this remarkable connection between BEC and U1 symmetry breaking. But how do they actually prove it? What kind of mathematical gymnastics are we talking about here?
The proof of Theorem 1.1 involves several intricate steps and clever techniques. It builds upon the groundwork laid by Proposition 1.1, but it introduces additional layers of complexity.
All right, I'm ready to delve into those complexities.
Yeah.
I have a feeling things are about to get pretty intense, mathematically speaking.
Indeed they do. Are you ready to explore the intricate world of perturbed grand potentials, C-number substitutions, and entropic inequalities?
Absolutely. Lead the way. Yeah. I know our listeners are eager to understand the mathematical machinery behind this groundbreaking result.
Okay. Let's start by discussing how they handle the perturbations. Remember, they introduced two perturbation parameters.
Right.
Lambda, which controls the strength of the symmetry breaking nudge, and delta, which serves a more technical role in fine-tuning the energy of the condensate.
Right. Two perturbations to probe the system's response.
Yeah.
What do they do with these perturbations?
The first step is to find upper and lower bounds for the perturbed grand potential, similar to what they did in Proposition 1.1. However, this time the calculations are, well, they're much more involved because they have to account for the effects of both lambda and delta.
I can imagine. How do they handle these extra complications?
For the upper bound, they modify their trial state. Remember that coherent state we talked about earlier for the condensate?
Yeah.
Well, they adjust its phase to align with the phase of the lambda perturbation.
So they're essentially syncing up their trial state with the direction of the symmetry breaking nudge.
Exactly. This ensures that their trial state captures the essence of how the condensate responds to this perturbation. For the lower bound, they utilize a multi-pronged approach. They combine Onsager's lemma, C-number substitution, and entropic inequalities to create a tight lower bound for the perturbed grand potential.
Whoa, that's a lot to unpack. Can you break down each of those techniques for us?
Certainly. Let's start with C-number substitution. It's a clever trick that simplifies calculations by replacing certain operators with ordinary numbers. In this case, they're focusing on the creation and annihilation operators for the zero momentum mode, which is where the condensate forms.
So instead of dealing with complicated operators, they're essentially replacing them with numbers. That seems like a risky move.
It might seem risky, but it's a well-established technique in quantum field theory. When a large number of particles occupy the same state, like in a BEC, these operators can be effectively replaced by numbers representing the average occupancy of that state.
I see. It's like treating the condensate as a classical field rather than a collection of individual particles.
Yes.
What about entropic inequalities? Where do those come into play?
Entropic inequalities are powerful tools from information theory that relate the uncertainty in a system's state to its energy. They provide crucial bounds on the system's behavior, allowing the authors to refine their estimates for the perturbed grand potential.
Okay, so they're combining C-number substitution and entropic inequalities to establish a lower bound for the perturbed grand potential.
All right.
What's the next step?
The next step involves differentiating the perturbed grand potential with respect to each of the perturbation parameters, lambda and delta. This differentiation allows them to isolate the effects of each perturbation and uncover the connections to BEC and symmetry breaking.
Differentiation, huh? It seems like we're going from thermodynamics to calculus now.
It might seem like a detour, but differentiation is a powerful tool for analyzing functions. By differentiating the perturbed grand potential, they can essentially zoom in on how each perturbation influences the system's energy and extract valuable information about the system's behavior.
I'm starting to get a sense of the mathematical depth involved here. They've set up this system, nudged it with these perturbations, and now they're using sophisticated mathematical tools to analyze its response. It's like they're performing a delicate surgery on the grand potential to reveal its hidden secrets.
That's a great analogy, and the insights they uncover are, well, they're truly remarkable.
Okay, I think we've covered a lot of ground in part one of this deep dive. We've explored the basic concepts of spontaneous symmetry breaking and the mean field Bose gas, delved into the details of proposition 1.1, and started unraveling the proof of theorem 1.1.
Indeed, we've laid a solid foundation for understanding this intricate connection between BEC and U1 symmetry breaking. Welcome back to our deep dive into this fascinating world of Bose-Einstein condensation and spontaneous symmetry breaking.
Okay, so let's pick up where we left off. We were just about to explore how the authors utilize differentiation to connect the perturbed grand potential to BEC and symmetry breaking.
Right, we've set the stage. We introduced those two perturbation parameters, lambda for the symmetry breaking nudge and delta for fine-tuning the condensate energy, and we established bounds for the perturbed grand potential. Now it's time for some calculus.
I have to admit, I'm a bit surprised to see calculus playing such a central role in this. It feels like we're jumping from thermodynamics to a whole different branch of mathematics.
It might seem like a leap, but calculus is an incredibly versatile tool. By differentiating the perturbed grand potential with respect to lambda and delta, the authors can isolate the effects of each perturbation and see how they influence the system's energy.
So it's like they're using differentiation as a magnifying glass to zoom in on the specific impact of each perturbation.
That's an excellent way to put it. Let's start with lambda, the symmetry breaking parameter. When they differentiate the perturbed grand potential with respect to lambda, they uncover a remarkable connection to the quasi-average of the creation operator.
Hold on, that's pretty significant, right? It means they're linking a thermodynamic quantity, the grand potential, to a quantum mechanical quantity, the quasi-average of the creation operator.
Precisely, and the implications are profound. They demonstrate that this quasi-average, which quantifies symmetry breaking, is non-zero precisely when the system exhibits BEC.
So their mathematical analysis goes beyond just observing BEC and symmetry breaking together. It reveals a deep intrinsic link between them in this system.
Exactly. It's a powerful result that strengthens our understanding of how these phenomena are intertwined. Now, to address the continuous behavior of the condensate fraction as they remove the perturbations, they differentiate the grand potential with respect to delta, the parameter that fine-tunes the condensate energy.
Okay, so by differentiating with respect to delta, they're essentially isolating the contribution of the condensate to the grand potential.
Precisely. By analyzing this derivative as delta approaches zero, they show that the condensate fraction changes smoothly without any abrupt jumps.
So the system gracefully transitions back to its unperturbed state. It's like watching a figure skater land a complex jump with perfect balance and control.
I like that analogy. It captures the elegance and stability of the system's response.
Okay, I think we've covered the high-level ideas behind their use of differentiation, but I'm curious about the specifics. Could you walk us through some of the mathematical details?
Certainly. Let's start with the derivative of the perturbed grand potential with respect to lambda. They express this derivative in terms of the expectation value of the sum of the creation and annihilation operators in the perturbed Gibbs state. This expression, combined with some careful analysis, allows them to extract information about the quasi-average of the creation operator.
I see. So they're using their knowledge of the perturbed grand potential and its derivatives to gain insights into the behavior of these quantum operators.
Exactly. They're bridging the gap between thermodynamics and quantum mechanics using the power of calculus. And the results speak for themselves. They rigorously demonstrate that the quasi-average is non-zero precisely when the system is in a BEC state, solidifying the link between BEC and symmetry breaking.
That's impressive. They're not just waving their hands and saying, hey, look, these two things happen together. They're backing it up with solid mathematical arguments. What about the derivative with respect to delta and its connection to the condensate fraction?
For delta, they follow a similar strategy. They express the derivative of the grand potential with respect to delta in terms of the expectation value of the number operator in the perturbed Gibbs state.
And the number operator is directly related to the condensate fraction, right? It tells us how many particles are occupying that zero momentum ground state.
Exactly. By analyzing the behavior of this derivative as delta approaches zero, they demonstrate that the condensate fraction changes continuously as they remove the perturbation.
Okay, that makes sense. So they're essentially using differentiation to pick apart the perturbed grand potential piece by piece and connect those pieces to the key players in this story, BEC and symmetry breaking.
That's a great summary. They're dissecting the system mathematically to reveal the intricate connections within.
Now, before we move on, I'd like to circle back to those C number substitutions you mentioned earlier. I understand they simplify the calculations, but can you give us a more concrete example of how they work in practice?
Certainly. Imagine you have an operator that creates a boson in the zero momentum state denoted by AA. In a BC, where a large number of bosons occupy this state, we can effectively replace this operator with a complex number, Z, that represents the amplitude and phase of the condensate.
So instead of dealing with an operator that creates a single boson, we're now dealing with a number that represents the collective behavior of the condensate.
Precisely. And a similar substitution is applied to the annihilation operator, A0, which is replaced by another complex number, Z. These substitutions allow them to transform the Hamiltonian, which initially involves complicated operator algebra, into a much more manageable expression.
I see. It's like they're translating a problem from a language of abstract operators to a language of familiar numbers.
That's an excellent way to think about it. And this translation allows them to leverage powerful tools from calculus and information theory to analyze the system's behavior.
Okay, I think I'm starting to grasp the power of C-number substitution. Now, you mentioned that they also use entropic inequalities to refine their lower bound for the perturbed grand potential. Can you elaborate on how these inequalities come into play?
Absolutely. Entropy, in the context of information theory, is a measure of uncertainty or disorder. Entropic inequalities establish relationships between the uncertainty in a system state and its energy.
So they're essentially using these inequalities to put constraints on the system's energy based on the level of uncertainty in its state.
Exactly. And these constraints prove invaluable in deriving a tight lower bound for the perturbed grand potential.
This is truly fascinating. It seems like they're drawing from a wide range of mathematical tools to tackle this problem.
Indeed, their approach is a testament to the interconnectedness of different branches of mathematics and their ability to shed light on complex physical phenomena.
Okay, I think we've explored the key mathematical techniques involved in this paper. Coherent states, Onsager's lemma, C-number substitution, and entropic inequalities. But before we wrap up part 2 of this deep dive, I'd like to revisit their key result, Theorem 1.1, and discuss its implications in more detail.
An excellent idea. It's important to step back and appreciate the significance of their findings and how they contribute to our understanding of the quantum world.
Okay, so Theorem 1.1 establishes this profound connection between BEC and U1 symmetry breaking. Can you remind us of the 3 parts of this theorem and their significance?
Certainly. Part A deals with the unperturbed system, meaning the system without the symmetry-breaking nudge. It states that this system undergoes a BEC phase transition at a specific critical temperature similar to the ideal Bose gas. They even provide a formula for the condensate fraction, the proportion of particles in the ground state.
So even without poking the system, we still see this BEC transition.
Yes, it's an inherent property of the mean field Bose gas. Now, part B is where the magic happens. It states that when they apply their quasi-average approach, the symmetry breaking is directly tied to the occurrence of BEC. Specifically, the quasi-average of the creation operator, a measure of symmetry breaking, is non-zero precisely when BEC occurs.
Hold on, that's a pretty big deal, right? It means BEC and U1 symmetry breaking are essentially the same thing in this system.
Precisely. It's a stunning connection that goes beyond just observing these phenomena together. It establishes a deep mathematical link between them. And finally, Part C adds another layer of intrigue. It states that the condensate fraction, how many particles are in that ground state, behaves continuously as the perturbation is removed.
So the system gracefully transitions back to its unperturbed state without any sudden jumps in the condensate fraction.
Exactly. It's like gently lowering the pencil back onto its tip. The system smoothly returns to its original state.
Now, you mentioned that they even derived a formula for the condensate fraction. Can you tell us a bit more about this formula and what it reveals about the system?
Absolutely. Their formula for the condensate fraction reveals that it depends on several key parameters: the temperature, the chemical potential, the interaction strength, and a constant related to the geometry of the system. What's particularly interesting is that this formula allows us to predict how the condensate fraction will change as we vary these parameters. For example, we can see how the condensate fraction increases as we lower the temperature or increase the interaction strength, which aligns with our intuition about BEC formation.
So their formula gives us a quantitative understanding of how the condensate fraction depends on the system's properties.
Precisely. It's a powerful tool that allows us to make predictions about the system's behavior and test those predictions against experimental observations.
This is truly remarkable. They've not only established a deep connection between BEC and symmetry breaking, but also provided us with a quantitative framework for understanding this connection.
Indeed. Their work significantly advances our understanding of the quantum world, pushing the boundaries of both theoretical and experimental physics.
Okay, I think we've thoroughly explored the depths of their mathematical analysis, from the perturbed grand potential and its derivatives to the ingenious use of C-number substitution and entropic inequalities. But I'm also eager to explore the broader implications of their findings.
I agree. Their work has far-reaching consequences that extend beyond the specific system they studied.
Excellent. Join us for part 3 of this deep dive as we discuss those broader implications, explore potential applications, and speculate on the future of this fascinating field of research. Welcome back to the deep dive. We've been on quite a journey exploring this intricate world of Bose-Einstein condensation and spontaneous symmetry breaking.
We certainly have. We've delved into the mathematical depths of Deutscher, Nahm, and Napier-Kautsky's paper. Unraveling their proof of the connection between BEC and U-boson symmetry breaking in the mean field Bose gas.
It's been fascinating to see how they combine tools from thermodynamics, quantum mechanics, calculus, and information theory to kind of build their argument. But now I'm curious about the bigger picture. What are the implications of their findings beyond this specific system?
That's a great question. While they focus on a theoretical model, the mean field Bose gas, their work has implications that reach far beyond this particular system. Their insights into the interplay of BEC and symmetry breaking can impact our understanding of a wide range of phenomena in condensed matter physics and even cosmology.
Okay, let's start with condensed matter physics. How could this research impact the study of materials?
Well, BEC and symmetry breaking, they play crucial roles in many exotic phases of matter, like superfluidity and superconductivity.
Right.
Superfluids, for example, flow without any resistance.
Yeah.
A mind-boggling phenomenon with potential applications in frictionless transport and energy transfer. Superconductors, on the other hand, can conduct electricity with zero loss, paving the way for incredibly efficient power grids and electronic devices.
So these are not just theoretical curiosities. They have the potential to revolutionize technology as we know it.
Exactly. And while superfluidity and superconductivity are observed in more complex systems than the mean field Bose gas, the underlying principles are deeply connected. The tools and techniques developed in this paper, they could be adapted and extended to study these more realistic systems, potentially leading to breakthroughs in material science and engineering.
Imagine designing new materials with enhanced superconducting properties based on these insights. It could be a game changer for energy transmission and storage.
Absolutely. The potential applications are vast and exciting. Now, let's shift gears and talk about cosmology. How could a paper about bosons on a donut-shaped space possibly relate to the vastness of the universe?
That's what I'm wondering. It seems like a giant leap from microscopic particles to cosmic scales.
It might seem like a stretch, but there's a surprising connection. Some theories suggest that the early universe, shortly after the Big Bang, was in a state very similar to a Bose-Einstein condensate. This primordial condensate, composed of exotic particles, is thought to have played a key role in the formation of the large-scale structures we observe today, such as galaxies and galaxy clusters.
So are you saying that studying these tiny bosons could help us unravel the mysteries of the early universe and the origins of these massive cosmic structures?
Exactly. The mathematics of BEC and symmetry breaking developed for systems like the mean field Bose gas can be applied to cosmological models, bridging the gap between the microscopic world of particles and the macroscopic realm of the cosmos.
That's truly mind-blowing. It speaks to the interconnectedness of physics across vastly different scales.
It does. Now, I want to highlight another important aspect of their work: the consideration of finite temperatures. Most theoretical studies of BEC focus on the zero temperature limit, where the system is perfectly ordered. However, real-world systems always have some thermal fluctuations. The authors explicitly consider positive temperatures in their analysis, which makes their results more relevant to experimental observations.
So they're not just working in an idealized theoretical world. They're bringing their analysis closer to reality.
Precisely. And what's remarkable is that they find the connection between BEC and symmetry breaking to be robust even at finite temperatures. It suggests that this link is not just a peculiarity of extremely low temperatures, but a fundamental aspect of these systems.
Okay, that makes their findings even more compelling. It means this connection likely plays a role in real-world systems, not just in theoretical models.
Exactly. Now, before we wrap up, I'd like to address a question that might be on our listeners' minds. The authors focus on U1 symmetry, which is related to particle number conservation. Are there other types of symmetries in physics, and could their methods be applied to study those as well?
That's a great question. It highlights the fact that U1 symmetry is just one example of a vast family of symmetries in physics. From rotational and translational symmetry to more abstract gauge symmetries, symmetries play a foundational role in our understanding of the universe.
Exactly. And wherever there's symmetry, there's the possibility of symmetry breaking. The beauty of Deutschert, Nam, and Napierkowski's work is that their methods are not limited to U1 symmetry. Their general approach of perturbing the system, analyzing the grand potential, and using techniques like scene number substitution and entropic inequalities can potentially be adapted to study other types of symmetry breaking as well.
So their work opens up new avenues for exploring symmetry breaking in a wide range of physical systems.
Precisely. It's a testament to the power of their approach and the deep insights it provides.
This has been an incredible journey. We started with a paper about bosons on a donut-shaped space and ended up exploring the connections between condensed matter physics, cosmology, and the fundamental role of symmetry in the universe.
It's been a thrilling ride, and I hope our listeners share our enthusiasm for this remarkable research.
I'm sure they do. It's a great reminder that even the most abstract theoretical work can have profound implications for our understanding of the world around us.
Absolutely. And it underscores the importance of supporting fundamental research, as it often leads to unexpected breakthroughs and expands the frontiers of human knowledge.
Well said. It's been a pleasure diving into this paper with you. I feel like I've gained a whole new appreciation for the power of theoretical physics and the beauty of mathematics.
The pleasure was all mine. Until next time, keep those minds curious, and who knows what other amazing discoveries await us in the depths of the scientific world.
That's right. And remember, you can always send us your requests for future deep dives. We're always eager to explore the fascinating world of science and share our findings with you. All right, welcome to another deep dive. This time we're taking a look at a paper that you sent over, a pretty recent one by Deutschert, Nam, and Napierkowski.
Yeah.
And it looks at Bose gases spontaneous symmetry breaking. A whole lot of math in there. So I've got our expert here to help us break it down.
Hello.
So the paper focuses on spontaneous symmetry breaking in a mean field Bose gas at positive temperature.
Yeah.
Let's start with the basics. Can you remind us what spontaneous symmetry breaking is all about, especially in this context?
Okay, so imagine we have a system governed by laws of physics, and these laws have a certain symmetry to them.
Okay.
But the system itself, in its lowest energy state, doesn't reflect that symmetry, so it's like the system is making a choice.
Okay.
Even though the underlying laws don't favor any particular outcome, a classic example is a ferromagnet.
Mm-hmm.
So the laws governing the springs in a magnet, they don't favor any particular direction
Right.
for the overall magnetization. But when we cool a magnet below a certain temperature, it spontaneously picks a direction to magnetize in, breaking the rotational symmetry.
Yeah, it's like the system picks a direction, even though, like you said, the laws treat all directions equally.
Exactly.
And that choice has real physical consequences, like leading to a magnet having a north and south pole. Now, how does this connect to Bose gases and the mean field approximation?
Okay, well, a Bose gas is a collection of particles called bosons, and they love to occupy the same quantum state.
Mm-hmm.
And at very low temperatures, a large fraction of these bosons condense into the lowest energy state, forming a Bose-Einstein condensate, or BEC.
Mm-hmm.
And this BEC, it exhibits a kind of order that wasn't present in the higher temperature gas.
Mm-hmm.
This transition from disorder to order is a form of spontaneous symmetry breaking.
Okay, so the BEC chooses a specific state, breaking the symmetry that was present in the higher temperature gas.
Mm-hmm.
Now, where does the mean field approximation come in?
Well, the mean field approximation simplifies things. Okay. It assumes that each boson interacts not with every other boson individually, but with an average or mean field created by all the other bosons.
Okay.
It makes the math a bit easier while still capturing the collective behavior of the bosons.
So it's like replacing like a complex dance floor where everyone is bumping into each other with like a smoother ballroom where everyone is just gliding along, influenced by the overall flow of the crowd.
Yeah, and this mean field approximation is particularly relevant when the interactions between bosons are relatively weak and long-ranged.
Okay, so we've set the stage. We have Bose gases that can undergo BEC, and we're using this mean field approximation to simplify the picture. Now let's dive into the specifics of this paper. They're looking at this very specific type of symmetry breaking, U1 symmetry breaking. What's so special about U1 symmetry?
Okay, so U1 symmetry is a type of continuous symmetry.
Okay.
And it's related to the conservation of particle number. You can think of it as a rotational symmetry in an abstract mathematical space. In the case of a Bose gas, this symmetry implies that the physics of the system shouldn't change if we shift the phase of the wave function,
Okay.
describing the condensate by a constant amount.
So it's like saying that rotating the entire condensate in this abstract space doesn't change the physical observables.
Yes.
But the paper claims that BEC is intimately linked to the breaking of this U1 symmetry. How does that work?
Well, that's the central question that the paper is addressing.
Okay.
Their key finding, Theorem 1.1, is a mathematically precise statement that BEC and the spontaneous breaking of U1 symmetry are equivalent in the context of a mean field Bose gas at positive temperatures.
So they're saying they're not just related, but they're like the same thing?
Exactly.
This theorem seems like the heart of the paper. Can you unpack it for us?
Okay. So Theorem 1.1 is a three-part statement,
Okay.
each providing a different perspective on this equivalence. The first part states that if there's BEC, meaning there's a macroscopic occupation of the zero momentum state, then U1 symmetry is spontaneously broken.
Okay, so if we see a BEC forming, with all those bosons piling to the same state, that's a telltale sign that U1 symmetry has been broken.
Yes.
What about the other parts of the theorem?
Okay, well, the second part goes the other way.
Right.
It says that if the U1 symmetry is spontaneously broken, then there must be BEC.
So it's a two-way street.
Yes.
Either phenomenon implies the other.
Exactly.
It's fascinating how these seemingly abstract mathematical concepts have such direct physical consequences. What's the third part of the theorem?
Okay, so the third part, it provides a precise quantitative relationship between the amount of BEC measured by the condensate fraction
Okay.
and the amount of U1 symmetry breaking, quantified by something called Bogoliubov's quasi-averages.
Now, you mentioned Bogoliubov's quasi-averages earlier.
Yes.
Can you explain what they are and why they're important here?
So, Bogoliubov was a physicist who developed a way to mathematically study systems with spontaneously broken symmetry. He introduced a tiny perturbation that explicitly breaks the symmetry.
Okay.
Then he studied the system as that perturbation vanished.
So it's like introducing like a tiny, tiny crack in a perfectly symmetrical vase
Yes.
to see how it affects the overall structure. But why even introduce this perturbation in the first place? Why not just study the system with the symmetry intact?
Well, by introducing this perturbation, you're giving the system a little nudge.
Okay.
Then you see how it responds as the perturbation gets smaller and smaller.
Okay.
If the symmetry is spontaneously broken, the system will remember that nudge.
Even though the perturbation is gone.
Exactly, even in the limit where the perturbation vanishes.
So it's like the system has a preference for a certain state, even though the underlying laws don't favor any particular state, and these quasi-averages capture this preference mathematically.
Exactly. They quantify how much the system deviates from the perfectly symmetrical state, even in the absence of that explicit symmetry-breaking perturbation.
Okay, so these quasi-averages are a measure of how broken the symmetry is.
Yes.
And the third part of Theorem 1.1 connects these quasi-averages to the condensate fraction,
Yes.
which tells us how many bosons are in the BEC. That's a pretty remarkable link.
Yes.
It highlights the fact that the formation of the DEC, with all those bosons piling into the same state,
Yeah.
it's tied to the breaking of the U1 symmetry.
Precisely.
The more bosons in the BEC, the more broken the symmetry is.
Yes.
This Theorem 1.1 is a pretty big deal then. It's not just a qualitative statement.
Yeah.
It's a precise mathematical relationship that connects BEC and U1 symmetry breaking. I'm guessing the proof of this theorem is where the really heavy mathematical lifting comes in.
Yes, the proof is quite intricate, but it involves some powerful mathematical tools. They use a variational approach to establish upper and lower bounds for the grand potential,
Okay.
both with and without the symmetry-breaking perturbation. And by carefully analyzing these bounds using the Hellman-Feynman theorem, they're able to extract that relationship between the condensate fraction and the Bogoliubov quasi-averages.
Okay, so we've got the big picture of the theorem, the strategy for the proof. But before we dive into the nitty-gritty of the proof, let's take a step back and just remind ourselves of the key concepts in BEC and U1 symmetry breaking. I think it'll help us appreciate the finer details of the proof when we get there.
Sounds good.
So let's start with the ideal Bose gas.
Okay.
It's a simplified model, but it already exhibits BEC. Can you remind us of the key features of the ideal Bose gas and how BEC emerges?
Well, the ideal Bose gas is a theoretical model,
Okay.
and it describes non-interacting bosons confined in a box. The only thing we need to consider is the kinetic energy of these bosons. At high temperatures, the bosons are spread out over a wide range of energy levels. But as we lower the temperature, more and more bosons start piling into the lowest energy state, which is the zero momentum state.
It's like a popularity contest where everyone wants to be in the coolest group.
Yeah.
And as it gets colder, that coolest group just becomes more desirable.
Exactly. And this piling up of bosons into the zero momentum state is BEC.
Okay.
There's a critical temperature below which a macroscopic fraction of the bosons occupy this single state.
And this critical temperature depends on the density of the bosons.
Exactly. The higher the density, the higher the critical temperature. This is reflected in the equation for the expected number of particles in each momentum state, and it involves a sum over all possible momentum states. And each term in the sum represents the average number of particles in that state. When the temperature goes below the critical temperature, this sum diverges for the zero momentum state,
Okay.
indicating a macroscopic occupation of that state.
So we have this equation that governs the distribution of bosons over the energy levels.
Yes.
And at low enough temperatures, this equation tells us that a huge number of bosons will cram into that zero momentum state, leading to BEC.
Yeah.
Now, how does this relate to U1 symmetry breaking?
Okay, so remember, U1 symmetry is related to the conservation of particle number. In the ideal Bose gas, this symmetry manifests as the invariance of the system under a global phase shift of the wave function.
Okay.
But when BEC occurs, the condensate wave function acquires a definite phase, breaking this U1 symmetry.
So before BEC, the system is like a spinning top.
Okay.
We can rotate it without changing anything. But once BEC forms, it's like the top is settled down. It's pointing in a specific direction.
Yes.
And rotating it now does change things.
Exactly. The BEC, by acquiring a definite phase, picks out a specific direction in that abstract mathematical space.
Breaking the rotational symmetry.
Yes.
Okay, I think we have a good handle on the ideal Bose gas and how BEC emerges and breaks the U1 symmetry in this model. But the paper goes beyond the ideal Bose gas. They're dealing with a mean field Bose gas. What changes when we introduce interactions between the bosons?
Well, introducing interactions makes things more complex. Instead of bosons just bouncing around freely, they now feel the presence of each other, which affects their energies and how they distribute themselves.
Okay.
But the mean field approximation allows us to simplify the picture by replacing all those individual interactions with an average interaction.
Right. So instead of each boson having to keep track of every other boson of the dance floor,
Yeah.
they're just responding to the overall vibe of the crowd.
Exactly. And this simplification allows us to write down equations that describe the behavior of the mean field Bose gas.
Okay.
One crucial equation is the Gross-Podolsky equation.
Okay.
It governs the condensate wave function in the presence of interactions.
So the Gross-Podolsky equation is our new tool
Yes.
for understanding how the condensate behaves when the bosons are interacting. And I'm guessing this equation plays a role in their proof of theorem 1.1.
It does.
Okay.
It's essential for understanding the energetics of the condensate and how it responds to that symmetry-breaking perturbation.
This is where things are starting to get really interesting. But I can already sense that we're just scratching the surface. There's a lot more to unpack here, especially when it comes to the mathematical details of the proof. Should we dive into those details now or save them for the next part of our deep dive?
I think it's best to save the deep dive into the mathematical details for the next part. We've laid a good foundation.
Okay.
And now we can appreciate the cleverness of the proof.
All right, sounds good. We'll leave our listeners on the edge of their seats, eagerly anticipating the next part of our deep dive into this fascinating paper.
Great. Welcome back. Are you ready to delve into the mathematical intricacies of the proof?
Absolutely. We've set the stage, explored the key concepts, and now it's time to roll up our sleeves and grapple with the equations.
Excellent. So, as we mentioned earlier, the authors employ a clever strategy to prove theorem 1.1. They establish both upper and lower bounds for the grand potential of the system,
Okay.
both with and without that tiny symmetry-breaking perturbation.
Right, it's like they're building a mathematical vice, squeezing the true value of the grand potential between these two bounds,
Yeah.
tighter and tighter, until they can extract that precise relationship between BEC and U1 symmetry breaking.
That's a great analogy. And the ingenuity lies in how they construct these bounds. For the upper bound, they utilize carefully chosen trial states that encapsulate the essential physics of the system.
Okay.
For the lower bound, they leverage the power of Onsager's lemma, which allows them to relate the grand potential of the interacting system to a simpler non-interacting system with an additional constraint.
So it's a delicate dance between physical intuition and mathematical rigor.
Yes.
Let's start with the upper bound. How do they go about constructing these trial states?
Okay, so in the unperturbed case, meaning without that explicit symmetry-breaking nudge, they use a trial state that's a tensor product of two parts. The first part describes the condensate,
Okay.
and for that, they use a coherent state, a quantum state that behaves much like a classical wave.
So it's like saying that the condensate, with all those bosons occupying the same state, starts behaving a bit like a macroscopic object,
Exactly.
losing some of its quantum fuzziness.
Exactly. And the coherent state is characterized by a complex number, z,
Okay.
which essentially tells us the amplitude and phase of this macroscopic wave. They carefully choose this z to minimize the energy of the condensate.
Okay, so that's the condensate part of the trial state. What about the other bosons that aren't part of the condensate?
Okay, so for the rest of the particles, they use a grand canonical Gibbs state. It describes a system in thermal equilibrium with a reservoir of particles and energy.
Right. The Gibbs state tells us the probability of finding the system in a particular energy state.
Yeah.
But how do they account for the fact that these non-condensate bosons are still interacting with each other?
They choose the chemical potential of the Gibbs state so that the total expected number of particles in the trial state matches the actual number of particles in the system. This ensures that their trial state accurately reflects the density of the gas.
So it's like adjusting the pressure in the system to get the right number of particles.
Exactly.
Okay. So they've carefully crafted this trial state to capture the essential physics of the condensate and the non-condensate particles. Now, how do they use this trial state to get an upper bound on the grand potential?
Okay, so the grand potential, often denoted by A, is a thermodynamic potential. It combines the energy of the system with its entropy and the chemical potential. It's a very useful quantity for studying systems that can exchange particles and energy with their surroundings.
Right. It tells us about the free energy of the system.
Yeah.
The energy available to do work.
Yes.
But how do they calculate the grand potential for this trial state?
Well, they use the definition of the grand potential, which involves calculating the expectation value of the Hamiltonian, the energy operator.
Okay. And the entropy of the state. For the condensate part, described by the coherent state, the calculation is relatively straightforward, using the known properties of coherent states.
And I'm guessing the calculation of the non-condensate part, described by the Gibbs state, is a bit more involved
Yes.
because they have to account for the interaction.
Exactly. Here they utilize a powerful tool from quantum field theory called Wick's theorem. This theorem allows them to break down complicated combinations of creation and annihilation operators into simpler products.
So it's like a mathematical power tool for quantum calculations.
It is. And by using Wick's theorem, they're able to manage the complexity of calculating the expectation values of those operator combinations, leading to an explicit expression for the grand potential of the trial state.
Okay, so they have an expression for the grand potential of this carefully constructed trial state.
Yes.
How does that give them an upper bound for the true grand potential of the system? Well, the key is that the true ground state of the system will always have a grand potential that's less than or equal to the grand potential of any other state,
Okay.
including their trial state.
So the trial state might not be the true ground state, but it gives them kind of a handle on the maximum possible value of the grand potential.
Exactly.
Okay.
And they meticulously go through the calculations, accounting for the energy contributions from the condensate, the non-condensate particles, and the interactions between them, arriving at an explicit formula for this upper bound.
So they have their upper bound.
Yes.
Now, how do they go about establishing the lower bound? This is where Onsager's lemma comes in, right?
Exactly. Onsager's lemma is a rather abstract tool, but it's incredibly powerful. In essence, it allows you to relate the free energy of a system with certain interactions to the free energy of a simpler system without those interactions,
Okay.
but with an additional constraint.
So it's like a trade-off. Complexity for constraint. They're simplifying the interactions,
Yes.
but adding a new rule that the system has to follow.
Precisely. And in this case, they apply Onsager's lemma to relate the grand potential of the interacting Bose gas to the grand potential of an ideal Bose gas, where the bosons don't interact at all.
Wait, so they're getting rid of the interactions entirely. How does that help them understand the original interacting system?
The trick is in the constraint. They introduce an additional term in the Hamiltonian of the ideal gas that mimics the average effect of the interactions in the original system. It's like replacing a detailed map of individual interactions with a simpler averaged out force field.
So they're not ignoring the interactions completely.
No.
They're just replacing them with a simpler average effect. And because the ideal Bose gas is much easier to handle mathematically, they can calculate its grand potential relatively easily.
Exactly. And that calculated grand potential for the ideal gas with that additional constraint serves as a lower bound for the grand potential of the original interacting system.
Okay, so they've squeezed the true grand potential of the interacting system between two bounds.
Yes.
An upper bound from that carefully constructed trial state and a lower bound from the cleverly constrained ideal gas.
Precisely.
What do they do with these bounds? How do they actually use them to prove theorem 1.1?
Okay, well, that's where the next stage of their strategy comes in. They repeat this entire process, establishing upper and lower bounds.
Okay.
But now they do it for the perturbed system, the one where they've introduced that tiny symmetry breaking nudge.
So they have four bounds now,
Yep.
upper and lower bounds for both the unperturbed and perturbed grand potentials.
Exactly.
What do they do with this mathematical arsenal?
Okay. Well, they bring in another powerful tool, the Hellman-Feynman theorem.
Okay.
This theorem relates the derivative of the energy of a system with respect to a parameter to the expectation value of the derivative of the Hamiltonian with respect to that same parameter.
Okay, that sounds pretty abstract.
Yes.
Can you break it down for us? How does it apply here?
Okay. So in this case, the parameter they're interested in is the strength of that symmetry breaking perturbation. The Hellman-Feynman theorem allows them to connect the change in the grand potential, which is a kind of energy with respect to the perturbation strength, to the expectation value of certain operators that characterize the condensate.
So by looking at how the grand potential changes as they tweak that perturbation,
Yes.
they can gain information about the condensate itself.
Exactly.
Like how many bosons are in it.
Precisely. And by carefully analyzing the derivatives of their upper and lower bounds for the grand potential, they're able to extract bounds on those key expectation values related to the condensate.
This is where the rubber meets the road,
Yeah.
right? You're using these bounds derived through a combination of clever trial states, Onsager's lemma, and the Hellman-Feynman theorem.
Yes.
To finally connect BEC and U1 symmetry breaking in a quantitative way.
Exactly. They meticulously work through the math, taking limits, applying inequalities, and performing algebraic manipulations, until they arrive at that beautiful relationship stated in Theorem 1.1. The condensate fraction, which measures the amount of BEC, is directly proportional to the square of the Bogoliubov quasi-average, which quantifies the amount of U1 symmetry breaking.
It's a testament to the power of combining physical insight with rigorous mathematical analysis.
Yeah.
They've woven together these diverse threads of mathematical tools to create a tapestry that reveals a deep connection between these two fundamental phenomena in the quantum world.
Indeed. The proof is quite intricate, but it's a masterpiece of mathematical physics, and it highlights the beauty and elegance of mathematics in describing and explaining the complexities of the physical world.
Okay, so we've journeyed through the key ideas of the proof. We've seen how they construct those upper and lower bounds, how they utilize Onsager's lemma and the Hellman-Feynman theorem, and how they ultimately arrive at that precise relationship between BEC and U1 symmetry breaking. But there's one piece of the puzzle we haven't talked about yet, the effective chemical potential, denoted by A. Poe-Kild.
Yeah.
It seems to play a crucial role throughout the paper. Can you shed some light on what it is and why it's so important?
You're right. The effective chemical potential is a key concept in their analysis. Remember, the chemical potential, usually denoted by mu, controls the average number of particles in a system.
Right. It tells us how eager the system is to accept new particles. But what makes the effective chemical potential different?
Okay. So the effective chemical potential takes into account the interactions between the bosons. In a mean field system, each boson doesn't just cede the external potential, it also feels an average potential due to all the other bosons around it.
So it's like adding a social pressure term to the chemical potential.
Yeah.
Reflecting the influence of the crowd on each individual boson.
That's a great way to think about it. And this effective chemical potential is related to the actual chemical potential through a rather interesting equation, equation 1.23 in the paper. It involves a sum over all momentum states, similar to the equation for the expected number of particles, but with an additional term that depends on the interaction strength.
So it's like the effective chemical potential adjusts itself to account for the social scene of the bosons?
Yes.
Depending on how strongly they're interacting?
Precisely. And analyzing this equation in detail, as they do in Appendix A, is crucial for understanding the behavior of the system in different regimes. They prove three important results in this appendix.
Oh, an appendix. Those are usually where the really juicy details hide?
Yes.
What are those three key results?
Okay, so first, they demonstrate that this equation for the effective chemical potential always has a unique solution within a specific range.
Ensuring that mentally is well-defined.
So they're making sure that this crucial quantity, the effective chemical potential, is mathematically sound.
Yes.
It's like checking the foundation of their theoretical building to ensure its stability.
Exactly. Then they analyze the behavior of Mathilde in the limit of a large number of particles, making specific assumptions about the scaling of the temperature and the actual chemical potential. This is where the concept of mean field scaling that we talked about earlier becomes crucial.
Right. The mean field scaling ensures that the interactions don't become too strong as the system gets larger.
Yes.
What do they find about Mathilde in this limit?
Okay. Well, they derive crucial bounds on Mathilde in terms of id and the particle number.
Okay.
These bounds essentially tell us how the effective chemical potential is constrained by the actual chemical potential and the density of the gas.
So even though the effective chemical potential is this adjusted quantity that takes into account the interactions,
they're showing that it's still tethered to the actual chemical potential and the overall density of the gas.
Exactly. These bounds are essential for controlling the behavior of the grand potential and ensuring that their proof of Theorem 1.1 holds up.
Okay, that's two key results from Appendix A. What about the third one?
Okay, so the third result is a a bound on the expected number of particles in the system, showing that it's proportional to the difference between the actual and effective chemical potentials.
So the bigger the difference between mu and mu tilde,
Yes.
the more particles we expect to find in the system. That makes sense because a larger difference means that the interactions are having a more significant effect, potentially leading to more particles being attracted to the system.
Precisely. This bound is crucial for understanding how the system's thermodynamic properties, like the grand potential, depend on the microscopic details of the interactions and the effective chemical potential.
Okay, so we've got a good handle on the effective chemical potential now. It's this this adjusted chemical potential that takes into account the interactions, and it plays a vital role in shaping the behavior of the system. We've also seen how the authors meticulously analyze its properties in Appendix A, deriving crucial bounds and ensuring its mathematical consistency.
Indeed. And it's this careful attention to detail, this rigorous analysis of every aspect of the problem that gives their proof of theorem 1.1 its strength and elegance. They've left no stone unturned, ensuring that their argument is built on a solid mathematical foundation.
It's like they've constructed a mathematical cathedral, with each equation and theorem a carefully placed stone, supporting the grand structure of their proof.
It's a beautiful analogy, and it's this rigor that makes their work so compelling and convincing. They're not just waving their hands and saying, "Trust us." They're providing a detailed, step-by-step mathematical argument.
It's a testament to the power of mathematics to illuminate the deepest mysteries of the physical world. Well, we've covered a lot of ground in this part of our deep dive. We've explored the intricacies of the upper and lower bounds for the grand potential, the clever use of Onsager's lemma, the power of the Hellman-Feynman theorem, and the subtle role of the effective chemical potential. But we haven't yet delved into the specific details of how they actually use these bounds to prove theorem 1.1. That's where the real magic happens, right?
Absolutely. The next part of our deep dive will focus on the final steps of the proof, where we'll see how all these pieces fit together, how those bounds are manipulated and analyzed to extract that precise relationship between the condensate fraction and the Bogoliubov quasi-average.
It's like we've gathered all the ingredients, prepared the tools, and now we're ready to cook up the main course, the proof of theorem 1.1. Our listeners are in for a treat. All right, we're back, ready to tackle the final steps of this intricate proof.
Yes.
We've laid the groundwork, explored the key concepts, built up this whole arsenal of mathematical tools. Now it's time to see how they all come together to prove that BEC and U1 symmetry breaking are truly two sides of the same coin.
You're exactly right. This is where the authors demonstrate their mathematical prowess, carefully weaving together those upper and lower bounds for the grand potential, the insights from Onsager's lemma, and the power of the Hellman-Feynman theorem to arrive at that elegant relationship stated in theorem 1.1.
All right. So remind me again, how do they use those bounds to actually prove something about BEC and symmetry breaking?
Okay, so remember they have 4 bounds, upper and lower bounds, for both the unperturbed grand potential without the symmetry breaking nudge and the perturbed grand potential with the nudge. The key is to analyze how these bounds change as they vary the strength of that perturbation.
So they're essentially tickling the system with this perturbation and watching how the grand potential wiggles in response. And by carefully analyzing those wiggles, they can extract information about the condensate and the broken symmetry.
That's a great way to visualize it. And the Hellman-Feynman theorem is their tool for connecting those wiggles to specific quantities related to the condensate.
Okay.
Namely, the expectation values of the creation and annihilation operators for the zero momentum state.
Okay, that's starting to ring a bell. So they take the derivative of their bounds with respect to the perturbation strength.
Yes.
And the Hellman-Feynman theorem tells them that this derivative is related to those expectation values.
Exactly. And those expectation values are precisely what they need to connect to the condensate fraction, which measures the amount of BEC, and to the Bogoliubov quasi-averages, which quantify the amount of symmetry breaking.
Okay, I'm following so far. But the details of how they actually manipulate those bounds and extract those expectation values, that's where things start to get a bit hazy for me. Can we walk through those steps a bit more slowly?
Absolutely. Let's start with the lower bound for the perturbed grand potential. This is where they make some clever use of Onsager's lemma combined with a technique called C-number substitution.
Now, Onsager's lemma, we've talked about that. It lets them relate the interacting system to a simpler non-interacting system with a constraint. But C-number substitution, that's a new one. What's that all about?
It's a mathematical trick where they replace the creation and annihilation operators for the zero momentum mode with complex numbers.
So instead of dealing with these abstract operators, they're just plugging in ordinary numbers.
Yes.
Why does that work? Doesn't that oversimplify things?
It does simplify things, but in a controlled way that captures the essence of what's happening. Remember, when BEC occurs, the condensate behaves a bit like a classical wave with a well-defined amplitude and phase. By replacing the operators with complex numbers, they're essentially treating the condensate as a classical field.
So it's like they're saying, hey, the condensate is acting so classical anyway. Let's just go all in and treat it like a classical variable.
Exactly. And this simplification allows them to analyze the lower bound in more detail. They combine Onsager's lemma with this C-number substitution and some inequalities involving the entropy of the system to arrive at an expression for the lower bound that can be analyzed using perturbation theory.
Perturbation theory, that's a classic tool for dealing with small changes to a system.
Right. And in this case, the small change is that symmetry breaking perturbation. By applying perturbation theory to their lower bound expression, they're able to extract a term that's proportional to the square of the Bogoliubov quasi-average.
Okay, so they've managed to fish out a term related to symmetry breaking from that lower bound. What about the upper bound? How do they handle that?
For the upper bound, they use a similar approach, constructing a trial state that's a tensor product of a coherent state for the condensate and a Gibbs state for the remaining particles. But now they have to be a bit more clever in choosing their trial state because they need to account for the phase of that symmetry-breaking perturbation.
Right. The perturbation is no longer just a nudge. It has a direction in that abstract mathematical space.
Yes.
So their trial state has to be aligned with that direction.
Exactly. They carefully choose the phase of their coherent state to minimize the energy of the system in the presence of the perturbation. Then they calculate the grand potential for this trial state using similar techniques as before, involving Wick's theorem and careful accounting of the interaction energy.
And by analyzing this upper bound, they're able to extract another term that's proportional to the square of the Bogoliubov quasi-average.
Precisely. So now they have two expressions, one from the lower bound and one from the upper bound, both proportional to the square of the Bogoliubov quasi-average.
And this is where the magic happens, right? They somehow combine these expressions to connect the quasi-average to the condensate fraction.
You're right. They use the fact that the true grand potential is sandwiched between these two bounds. By carefully analyzing the difference between the upper and lower bounds and taking the limit as the perturbation strength goes to zero, they're able to isolate a term that directly relates the condensate fraction to the square of the Bogoliubov quasi-average.
That's amazing. They've managed to extract this precise relationship from those seemingly abstract bounds. It's a testament to the power of careful mathematical analysis.
It is. And this relationship is the heart of Theorem 1.1. It shows that the amount of BEC measured by the condensate fraction is directly proportional to the amount of U1 symmetry breaking quantified by the Bogoliubov quasi-average.
So the more bosons in the condensate, the more broken the symmetry is.
Yes.
It's a beautiful and elegant result, and it's all thanks to this intricate mathematical framework that they've built, using trial states, Onsager's lemma, the Hellman-Feynman theorem, and some clever manipulations of inequalities and limits.
Their work is a testament to the power of mathematical physics. They've taken this seemingly abstract concept of spontaneous symmetry breaking and connected it to a very concrete physical phenomenon, the formation of a Bose-Einstein condensate.
It's a reminder that the world of mathematics is not just a collection of abstract symbols and equations. It's a language that can be used to describe and explain the deepest mysteries of the universe.
Absolutely. And this paper is a shining example of how that language can be used to illuminate the fascinating interplay between symmetry and order in the quantum world.
Well, this deep dive has been quite a journey. We've explored the concept of spontaneous symmetry breaking, delved into the intricacies of the mean field Bose gas, and witnessed the power of mathematical tools like Onsager's lemma and the Hellman-Feynman theorem. And to our listeners, we hope this deep dive has sparked your curiosity and inspired you to explore further. The world of quantum physics is full of wonders waiting to be uncovered. Until our next deep dive, keep exploring. All right, so today we're diving headfirst into some serious quantum physics.
Buckle up.
We've got this paper, hot off the press, literally published today, February 3rd, 2025. It's called A Note on Spontaneous Symmetry Breaking in the Mean Field Bose Gas.
Catchy title.
It is.
Yeah.
Authored by Duchard, Nam, and Napiorkowski. And let me tell you, it's a wild ride through some heavy-duty mathematics.
Oh, yeah. Definitely not for the faint of heart. But that's why I'm here, Valerie, to help break it down.
You got it. So, big picture, what's this paper all about?
Well, it tackles a pretty fundamental question. How does Bose-Einstein condensation, BEC for short, relate to the concept of spontaneous symmetry breaking?
Two big hitters in the quantum world. We're talking about a system of interacting bosons, right?
Yep, exactly.
And not at absolute zero, at a positive temperature.
Right. Now, the mean field part, that's a simplification, a way to make the math a bit more manageable. Basically, you assume each boson interacts with a sort of average field created by all the other bosons.
So instead of calculating individual interactions, we're averaging it out. Smart.
Makes a huge difference. Now, I'm assuming you're familiar with BEC. This is where a macroscopic number of bosons all pile into the same quantum state at super low temperatures.
Right. They condense into the lowest energy state like a bunch of penguins huddling together for warmth.
Love the analogy. And in a translation invariant system, the lowest energy state, that's the zero momentum mode.
Okay, so that's BEC in a nutshell. Now, where does this symmetry breaking business come in?
Well, the paper focuses on a specific kind of symmetry called U1 symmetry. It's related to the conservation of particle number.
Meaning the total number of particles in our system that stays constant, right?
Exactly. But here's the thing. When you have BEC, a huge chunk of those particles are all in that zero momentum state.
So they're not spread out evenly. They've chosen to clump together in one specific state.
And that, my friend, can be seen as a form of symmetry breaking. The system had the potential to be symmetric, with particles evenly distributed, but it prefers this specific configuration.
So the system breaks the symmetry, even though the underlying laws are still symmetrical. Trippy.
Right. It's as if the universe had a choice, and it went with the option that looks less symmetrical. Now, this paper doesn't just say, hey, there's a connection. These authors actually prove it mathematically.
Oh, I bet they did. And I'm guessing it's not a simple proof.
Not exactly a walk in the park, no, but it's brilliant. They prove that in this mean field Bose gas, the onset of BEC is mathematically equivalent to the breaking of this U1 symmetry.
Two sides of the same quantum coin. How do they even begin to prove something like that? What's their approach?
They use something called Bogoliubov quasi-averages. It's a way to capture this idea of symmetry breaking mathematically.
Okay, quasi-average. Sounds intriguing.
It's a two-step process. First, you imagine adding a tiny, tiny perturbation to the system's Hamiltonian. This little nudge slightly breaks the U1 symmetry.
Like a tiny push on a perfectly balanced seesaw.
Perfect analogy. Then you take something called the thermodynamic limit. Basically, you let the system become infinitely large. This smooths out any fluctuations.
So you're focusing on the overall behavior, not tiny little random quirks.
Exactly. And by analyzing this perturbed system in the thermodynamic limit, you can see if the U1 symmetry is truly broken.
Meaning, does the system remember that initial nudge, even when it becomes infinitely large?
That's the question. If it does, then the symmetry was spontaneously broken. The system chose a specific state, even though it had the option to be perfectly symmetrical.
So how do these quasi-averages tie into BEC specifically?
It's through something called the one-particle density matrix. This matrix describes how the particles are distributed in the system.
Okay, so its elements tell us, like, how many particles are in each state.
In a way, yes. And its largest eigenvalue that tells us how many particles are in the most popular state.
Which in BEC would be that zero momentum state, right?
Bingo! Now, the authors show that the limit of this largest eigenvalue, as the system gets bigger and bigger, is directly related to the limit of those Bogoliubov quasi-averages.
Ah, so if those quasi-averages show symmetry breaking, this eigenvalue becomes macroscopic, meaning a huge number of particles are all in that one state.
And that's BEC. So they've linked these two seemingly separate concepts, symmetry breaking and BEC showing they're fundamentally intertwined.
Okay, that's a big deal. But I'm sure they didn't stop there. They had to prove this mathematically, right?
Oh, absolutely. They go deep into the mathematical weeds. They use a sophisticated variational approach to rigorously bound the system's grand potential.
Grand potential. Sounds grand. Remind me what that is again.
Think of it as a function that describes the system's energy, taking into account its internal energy and entropy.
So it's a way to quantify the system's preference for certain states, right?
Exactly. By minimizing the grand potential, we find the most stable state, the one the system naturally wants to be in.
Okay, I'm with you. And to find this minimum, they use a trial state, right?
Right, like a starting guess for the system's true state. They construct a trial state that has two parts, one representing the condensate, and the other representing the thermally excited bosons.
So they're modeling both the organized condensate and the rowdy particles that aren't part of it.
Love the way you put that. This trial state is cleverly designed. It has the same expected number of particles in the zero momentum mode as the real system, makes the analysis much simpler.
Smart move. And to refine things even further, they bring in coherent states, right?
Yes. Coherent states are special quantum states that behave a lot like classical waves.
So they're bridging the gap between the quantum world and the familiar world of waves.
Exactly. These coherent states capture the synchronized behavior of all those bosons in the condensate.
Okay, so they've got the condensate handled. What about those rowdy bosons that aren't condensed?
For those, they use the excitation Fock space. It's a framework for describing the possible states of those thermally excited particles.
So they've got a mathematical handle on both the organized and chaotic parts of the system.
And to top it all off, they use a technique called the C-number substitution. It's a way to simplify the problem by treating certain operators in the Hamiltonian as if they were regular numbers.
So they're sneaking in some classical physics to make the quantum calculations easier.
You got it. This trick allows them to derive even tighter bounds on that grand potential. They're pulling out all the stops.
Impressive stuff. And all of this leads up to their big result, Theorem 1.1.
The heart of the matter, absolutely.
So what does this theorem actually say? Break it down for me.
Well, it's got three parts, each highlighting a different aspect of the connection between BEC and symmetry breaking. Let's start with part A, shall we?
Lead the way.
Part A focuses on the unperturbed system, the one without that little nudge we talked about. It shows that this system actually undergoes a BEC phase transition at a specific critical temperature, just like the ideal gas model.
So even without us messing with its symmetry, the system can spontaneously condense at the right temperature.
Exactly. It's a fundamental behavior of these bosons. And the authors actually provide a formula for the condensate fraction. It tells you what proportion of bosons are in the condensate at a given temperature.
So like a quantum head count, basically.
Yeah.
Okay, what about part B? This is where things get really interesting, right?
Oh, yeah. This is where the Bogoliubov quasi-averages come into play. Part B shows that the limit of these quasi-averages, as the system gets infinitely large and we remove that tiny perturbation, is directly proportional to the square root of the condensate fraction.
Hold on, square root. Why the square root?
Good question. It's a consequence of how the quasi-averages are defined and how they relate to the condensate fraction mathematically. It's a bit involved, but the key takeaway is that the degree of symmetry breaking that's reflected in those quasi-averages is directly linked to the strength of the condensate.
So a large condensate fraction means we have significant symmetry breaking, and vice versa. They're two sides of the same coin.
Exactly. It's a beautiful connection. Now, part C, this one focuses on what happens to the condensate fraction as we remove that perturbation.
So we're basically undoing that little nudge we introduced earlier.
Right. And what the authors show is that the condensate fraction in the perturbed system smoothly approaches the condensate fraction of the unperturbed system as the perturbation strength goes to zero.
So there are no sudden jumps or weird discontinuities.
Nope, it's a smooth transition. This further strengthens the link between BEC and symmetry breaking. It shows that the condensate fraction is well behaved even when we mess with the system's symmetry.
Okay, so Theorem 1.1 is basically saying that BEC and symmetry breaking are two different ways of looking at the same underlying phenomenon.
Exactly. They're intertwined at a fundamental level. And the proof of this theorem, it's a real tour de force. The authors use a whole arsenal of mathematical techniques to make their case.
Well, let's dive into that proof then. I'm ready to see how they connect all the dots.
All right, let's start with part A of Theorem 1.1, which establishes the connection between the condensate fraction and the macroscopic occupation of the zero momentum mode in the unperturbed system.
The unperturbed system. So this is the one without the nudge, right?
That's right. The authors are essentially aiming to prove the second equality in equation, 1.28. They want to show that the fraction of particles in the zero momentum mode converges to the expected value based on the self-consistent ideal gas model as the system size grows.
Okay, so they're comparing their model to the ideal gas model as a benchmark.
Exactly. To do this, they start with the perturbed grand potential theta, delta lambda Robiler, focusing on the unperturbed system. Equation 3.3 lets them express the derivative of this potential with respect to delta as 0 bidzal delta deal delta beta.
Okay, so they're looking at how the grand potential changes when they tweak a parameter, delta in this case.
Right. This derivative reflects how sensitive the grand potential is to changes in this parameter. And the term on the right-hand side, text 2 beta, represents the expected number of particles in the zero momentum mode.
So the derivative tells us how the energy of the system changes when we adjust delta, and the right-hand side tells us about the number of particles in the condensate.
You got it. Now, a crucial ingredient here is the Gibbs variational principle. This principle tells us that the map, delta mapsto beta mu, is concave.
Concave, meaning it curves downwards like a bowl.
Precisely. This concavity is important because it lets us establish bounds on the derivative. For any delta we have fracta beta, beta mu theta mu co delta beta.
So the expected number of particles in the zero momentum mode is sandwiched between two expressions involving the grand potential.
Exactly. And by carefully selecting the value of the delta and using the bounds on the perturbed grand potential from proposition 3.1, they can constrain the expected number of particles in the zero momentum mode between two quantities that converge to the same limit as the system grows large.
So they are using the bounds to squeeze the number of particles in the condensate towards the desired value.
Precisely. They set delta for some alpha between 0 and 16, making sure that those error terms in proposition 3.1 become sufficiently small. This choice ensures that the upper and lower bounds in the inequality converge to the same value as eta, the system size, goes to infinity.
Okay, so they're carefully controlling the error terms to make sure their result is robust.
Exactly. Combining this with proposition 1.1 and the known behavior of the condensate fraction in the ideal gas model, as seen in equation 1.19, they arrive at the result. 1 potato NC, 1 peta 2 plus dad.
So they've successfully proven the second equality in equation, 1.28. But we're not done with part A yet, right?
You are absolutely right. We still need to prove the first equality in equation, 1.28, which relates the largest eigenvalue of the one particle density matrix to the fraction of particles in the zero momentum mode.
Right. That first equality is crucial for linking the mathematical formalism of the density matrix to the physical concept of BEC.
Exactly. And to prove this, they need to show that for any non-zero momentum P, the expected number of particles in that mode is negligible compared to the total number of particles.
Meaning almost all the particles are in the zero momentum state, which is the condensate.
Precisely. Mathematically, that means they need to demonstrate that text-strapped apides 2 bia.
So the number of particles in any other momentum state should become insignificant compared to the total number of particles as the system grows large.
Right. To prove this, they cleverly employ another tool from their mathematical arsenal, the Hellman-Feynman theorem. They introduce a small perturbation, epsilon apol, to the system's Hamiltonian, and analyze the difference in the grand potential to bound the expected number of particles in the p momentum mode.
Okay, so they're introducing another perturbation, but this time it's specifically targeting a different momentum state.
Yes. This is a targeted perturbation to see how the system responds to changes in the occupation of a specific momentum mode other than the zero momentum mode. Let's define a new grand potential functional, g epsilon, that incorporates this perturbation. Epsi beta, epsilon epsilon.
Yeah.
So this new grand potential takes into account the effect of adding or removing particles from the p momentum state.
Precisely. And the beauty of this approach is that the expected number of particles in the p momentum mode can be directly related to the difference in grand potentials with and without the perturbation.
G beta mu.
I see. So by analyzing the difference in these grand potentials, they can get a handle on the number of particles in the p-momentum state.
Exactly. They use the upper bound from proposition 2.1 and a modified lower bound from proposition 2.2 adapted to accommodate the new perturbation. This gives them a constraint on epsilon textrat, 1 epsilon texilon plus O, right.
Okay.
That
Okay, so they've squeezed the expected number of particles in the p-momentum state between two bounds. What's the next step?
Now comes the clever part. They examine what happens as epsilon approaches 0. Notice that the right-hand side of the inequality becomes of order O as epsilon goes to 0.
So as the perturbation to the p-momentum state vanishes, the number of particles in that state becomes negligible compared to the total number of particles.
Exactly. To show this rigorously, they carefully apply calculus. They examine the derivative of the function beta epsilon people with respect to epsilon and utilize the fact that tilde mu moon. They bound the difference in the logarithmic terms by a constant that's independent of data.
Okay, so they're using calculus to make sure that their bounds are tight and that the error terms are under control.
Precisely. And by choosing a suitable value for epsilon, such as epsilon 1412, they arrive at the desired conclusion. P-text date. This means that the expected number of particles in any non-zero momentum mode is indeed negligible compared to the total particle count, solidifying the picture that most of the particles are in the zero momentum mode, the condensate.
Fantastic. So they've successfully proven the first equality in equation, 1.28, completing the proof of part A. What's next?
Next, let's move on to part C of theorem 1.1, which examines the behavior of the condensate fraction in the perturbed system as the perturbation strength lambda approaches 0.
So now we're bringing back the nudge, that symmetry-breaking perturbation, and seeing how the condensate fraction changes as we make the nudge smaller and smaller.
That's right. The goal here is to show that the condensate fraction in the perturbed system smoothly converges to the condensate fraction of the unperturbed system as lambda goes to 0, as expressed in equation 1.30. Essentially, we want to show that the nudge doesn't fundamentally alter the condensate fraction in the long run.
Makes sense. If the connection between BEC and symmetry breaking is robust, then we'd expect the condensate to behave nicely even as we tweak the perturbation.
Exactly. And their approach to proving this mirrors their strategy in proving the second equality in part A. They utilize the concavity of the perturbed grand potential, those bounds from proposition 3.1, and a strategic choice of parameters to constrain the condensate fraction in the perturbed system and show its convergence to the desired limit as lambda goes to 0 and edit approaches infinity.
Okay, so they're using a similar strategy of carefully bounding the condensate fraction between converging quantities. Can you walk me through the specifics?
Absolutely. They analyze the perturbed grand potential, v lambda, delta, and just like before, they express the derivative of this potential with respect to delta big partial delta beta. So this derivative is telling us about how the energy of the perturbed system changes as we adjust the parameter delta.
Importantly, the term textry A0G beta represents the condensate fraction in the perturbed system. Now, using the concavity of the map, delta maps to v lambda, delta mu, which again stems from the Gibbs variational principle, they establish bounds for any delta beta. So once again, they've sandwiched the condensate fraction between two expressions involving the perturbed grand potential. I'm starting to see a pattern here.
Indeed, there's a beautiful symmetry in their approach. And just like before, they strategically choose delta lambda and apply proposition 3.1 to express the condensate fraction in the perturbed system as left data, A0, diabolita tilde gata, pelka data, product tilde hilda, tilde right, like data.
Okay, so they've expressed the difference between the perturbed condensate fraction and the unperturbed condensate fraction in terms of a bound that involves lambda in tau.
Exactly. And as lambda approaches 0 and edel approaches infinity, the right-hand side of this inequality goes to 0. This beautifully demonstrates that the condensate fraction in the perturbed system smoothly converges to the condensate fraction of the unperturbed system as the perturbation vanishes.
So the condensate fraction is well behaved, just as we expected.
Precisely. And combining this result with proposition 1.1 and the behavior of the condensate fraction in the ideal gas model, they arrive at lim tappa 1000 duo, lim tappa 30c, o mu 0, 0, lambda textile n beta plus trifecta, right? 1 kappa 32 plus $. This confirms the continuity of the condensate fraction as the perturbation vanishes, further reinforcing the connection between BEC and symmetry breaking.
Excellent. We've tackled Part C. Now, on to the grand finale, Part B, which you said was the most intricate part of this theorem.
Ah, yes, Part B, the heart of the matter. This is where we directly connect the Bogoliubov quasi-averages to the condensate fraction in the perturbed system, proving equation 1.29.
Bring it on. I'm ready for the challenge.
All right, but buckle up, because this is going to be a bit of a mathematical roller coaster. The proof relies on the concavity of a perturbed grand potential, those ever-reliable bounds from proposition 3.1, a strategic choice of parameters, and the trusty Cauchy-Schwarz inequality. We're bringing out the big guns.
Sounds intense, but I'm all ears. Let's hear it.
First, we have to acknowledge a helpful simplification. The Cauchy-Schwarz inequality actually implies that the results of Part C directly lead to the results of Part B when kappa
Hold on. Remind me what kappa represents again.
Kappa is a key parameter in this paper. It essentially captures the ratio of the system's temperature to its critical temperature for BDC. So when kappa at 11, we're in the non-condensed regime, meaning the temperature is too high for a significant condensate to form.
Right. So in this non-condensed regime, the Cauchy-Schwarz inequality helps us out, and we don't need to do any extra work for Part B.
Exactly. The real challenge comes when we consider the condensed phase, where kappa 11, because this is where we have a significant fraction of bosons occupying the zero momentum state, the condensate.
Okay, so we're focusing our attention on the condensed phase where the real action is happening. What's the next step?
We turn our attention to the perturbed grand potential for lambda, setting delta dollars this time. This choice focuses specifically on the effect of the symmetry-breaking perturbation, that nudge we've been talking about.
So we're zeroing in on how that nudge affects the system's energy landscape. Makes sense.
And to analyze this effect, the authors do what they do best. They take a derivative. They look at the derivative of the perturbed grand potential with respect to lambda, the strength of the perturbation. Factual lambda plus wa beta meta pexchi. Factual lambda plus sabo lambda plus omega and beta meta.
Okay, so they're seeing how the energy of the perturbed system changes as we crank up or down the strength of that symmetry-breaking nudge.
Precisely. Now, let's break down this equation. On the left-hand side, we have the derivative telling us about the sensitivity of the perturbed grand potential to changes in lambda. And on the right-hand side, we have some familiar players, meta, the total number of particles, and a term involving the trace of an operator.
Right, that trace term looks a bit intimidating, but it's essentially an expectation value, right?
You're absolutely right. It represents the expectation value of the operator $A plus Euler in the perturbed system. And remember, $A and $T are those creation and annihilation operators that create and destroy particles in the zero momentum state, the condensate.
Ah, so this expectation value is telling us something about the average behavior of particles entering and leaving the condensate.
Exactly. And here's where the Bogoliubov quasi-averages come in. Remember, these quasi-averages are essentially the limits of these expectation values as the system size grows infinitely large and the perturbation strength goes to 0.
Okay, so we're starting to see the connection between this equation and the quasi-averages we're trying to analyze in Part B.
We're getting there. Now, to make progress, we need to exploit the concavity of the perturbed grand potential. Remember, the Gibbs variational principle tells us that lambda maps in beta is a concave function.
Right, concave like a bowl. So what does that buy us?
Concavity lets us establish some handy bounds, just like we did in Part A, for any epsilon dollars we have. Beta mu lambda plus epsilon, beta mu sir 1, beta plus ado, g beta epsilon.
So we've sandwiched the expectation value we're interested in between two expressions involving the perturbed grand potential at different values of lambda.
Exactly. And just like in Part A, we're going to make a strategic choice for epsilon. This time, we set epsilon lambda 2, 2.
I'm sensing a theme here. Carefully choosing parameters to make those bounds work for us.
You got it. Combining this choice of epsilon with the bounds on the perturbed grand potential from proposition 3.1 allows us to express the expectation value of Ag plus Ag plus A0 plus Ag, right? A lambda 0 plus Ag beta plus A0 plus Ag at that A0 lambda plus A0 plus Ag.
Okay, so we've got another inequality involving the expectation value, the number of particles, the condensate fraction, and some terms involving lambda and weta. Where do we go from here?
The key now is to focus on what happens in the limit as lambda approaches 0 and beta approaches infinity. Notice that the right-hand side of this inequality vanishes in this limit.
So we're squeezing the left-hand side towards 0 as the perturbation goes away and the system size grows.
Exactly. To make this convergence more explicit, the authors divide both sides by squared n beta and take those limits, resulting in.
This is looking very promising. We're getting closer to equation 1.29, but I still see a difference. This equation involves the expectation value of 1 to plus 8r, while equation 1.29 focuses on the absolute value of the expectation value of $t. How do we bridge that gap?
Excellent observation. To complete the proof, we need to relate these two expectation values. We'll do this by considering the behavior of the condensate fraction in the limit lambda to dollars, which we established in part C.
Okay, so we're bringing in our previous result to help us out here.
Exactly. Let's define a complex quantity fractio g beta. This quantity lambda a essentially represents the normalized expectation value of the annihilation operator $t in the perturbed system. Think of it as a measure of how much the condensate is depleted by the action of this operator.
Okay, so it's capturing how many particles are being removed from the condensate, on average, normalized by the total number of particles.
Precisely. And from our previous result, we know that lambda's he is GO plus, so as the perturbation strength vanishes and the system becomes infinitely large, the real part of this normalized depletion measure approaches a value determined by kappa plus.
Right, kappa again being that crucial parameter that tells us if we're in the condensed regime or not.
Exactly. Now, to connect this to the expectation value of a plus 8, we bring in another powerful tool, the Cauchy-Schwarz inequality. This inequality provides an upper bound on the magnitude of lambda a chi beta and e gita. So we've bounded the magnitude of our depletion measure in terms of the expectation value of 80 Cheller, which is related to the number of particles in the condensate.
Okay, so the Cauchy-Schwarz inequality is helping us relate these different quantities.
Precisely. And now, using the result from part C and taking the limits lambda to 8 to ag theta, we get 1 kappa 32 plus. So the limiting magnitude of our depletion measure is bounded by a value determined by kappa.
Okay, I'm starting to see the pieces coming together.
We're almost there. Combining this inequality with our previous result for the real part of lambda, we arrive at a crucial conclusion. The imaginary part of lambda must vanish in the limit.
Oh, so we've essentially squeezed the imaginary part of our depletion measure to 0. But how does this help us prove equation 1.29?
This is the final piece of the puzzle. The vanishing imaginary part implies that the limit of the absolute value of the expectation value of $2 is equal to the limit of the real part of a lambda. And remember, lambda is directly related to the expectation value of $2. Therefore, we can finally write down equation 1.29, 1 code 212.
Wow, we made it. Part B is officially conquered. The authors have meticulously established the connection between those Bogoliubov quasi-averages and the condensate fraction in the perturbed system. What a journey.
It's truly remarkable how they were able to weave together so many different mathematical tools to build such a compelling argument. This is a testament to the power of rigorous mathematical reasoning in illuminating the subtle workings of the quantum world.
I'm exhausted, but I feel like I have a much deeper understanding of this connection between BEC and symmetry breaking now. It's not just a hand-wavy argument. It's backed by some serious mathematical firepower.
Exactly. This isn't just about abstract math either. This connection has deep implications for our understanding of a whole range of physical phenomena, from the behavior of superfluids to the origins of mass in fundamental particles.
That's what I love about physics. It's a constant interplay between theory and experiment, between abstract math and concrete reality.
I couldn't agree more, and this paper is a beautiful example of that interplay, showing how mathematical rigor can lead to profound insights into the workings of the universe.
Well, I think we've earned a break after that intense mathematical workout. But before we wrap up, I'm curious to hear more about those broader implications you mentioned. How does this research connect to other areas of physics, and what potential applications could it have?
Those are fantastic questions, and I'd love to delve into them, but perhaps we should save that for the next part of our deep dive. Give our listeners a chance to digest all this amazing math we've just explored.
That's a great idea. We'll pick up the conversation in part 3, where we'll explore the wider implications of this research and its potential to revolutionize our understanding of the universe. All right, we're back and ready to shift gears a bit.
From equations to implications, right?
Exactly. We spent the last two parts really digging into the mathematical nitty-gritty of this paper.
And it was worth it. Theorem 1.1, it's a powerful result, linking BEC and spontaneous symmetry breaking in a really elegant way.
No doubt. But now I'm curious, what does it all mean? How does this change the way we think about BEC, and what doors does it open for future research?
Well, for starters, it gives us a fresh perspective on Bose-Einstein condensation itself.
Right, we're not just counting particles in the zero momentum state anymore.
Exactly. We're now thinking about BAC as a consequence of the system's preference to break a fundamental symmetry. Even though the underlying laws are perfectly symmetrical, the system chooses a specific state that looks less symmetrical.
It's a subtle but profound point, isn't it? This idea that nature can spontaneously break symmetry.
Absolutely. And it's not just a theoretical curiosity. This idea of symmetry breaking pops up all over physics, from condensed matter to particle physics.
So this paper, by connecting BEC to symmetry breaking, might be hinting at some deeper, more universal principle at play.
That's the exciting possibility. It suggests that BEC might be more widespread than we previously thought.
Like, we might find it in systems where the traditional measures of condensate fraction don't quite tell the whole story.
Exactly. By looking for signatures of symmetry breaking, we might uncover new examples of BEC hiding in plain sight.
That's pretty cool. It's like we've been given a new lens to view the quantum world, and suddenly we're seeing things we didn't even know were there.
And it's not just about finding new examples of BEC. This connection to symmetry breaking also sheds light on the mechanisms behind BEC.
Meaning, we can understand why BEC happens in terms of this deeper principle of symmetry breaking.
Precisely. And that understanding can lead to new insights, new predictions, new ways to control and manipulate BECs.
This is where things start to get really interesting, right? The potential applications. You mentioned earlier that this research could help us understand exotic states of matter, like superfluids and supersolids.
Oh, yeah. Those are some of the most mind-bending phases of matter out there. Superfluids, they flow without any resistance, defying gravity and squeezing through impossibly small spaces.
It's like they're playing by a different set of rules, ignoring the friction and viscosity that govern ordinary fluids.
Exactly. And supersolids, they're even weirder. They have the rigidity of a solid, but they can also flow like a superfluid, passing through obstacles without any friction.
It's like imagining a block of ice suddenly deciding to flow through a narrow pipe without melting.
It's a truly bizarre concept, but it's real. And the key to understanding both superfluidity and supersolidity lies in Bose-Einstein condensation. These exotic states of matter emerge when bosons condense into a single quantum state.
So this paper, by giving us a new way to think about BEC, also gives us a new way to think about these exotic phases of matter.
Precisely. Instead of just focusing on the number of particles in the condensate, we can now think about superfluidity and supersolidity in terms of the system's choice to break a fundamental symmetry.
And that can lead to new insights into why these systems behave so strangely.
Absolutely. It might even help us discover new types of superfluids and supersolids with even more mind-boggling properties.
Okay, so we've got potential implications for fundamental physics and potential new states of matter to discover. What about practical applications? Can this research lead to any real-world technologies?
Definitely. One area where BECs are already being explored is quantum computing.
Right, quantum computers, those super powerful machines that exploit the weirdness of quantum mechanics to solve problems that are impossible for classical computers.
Exactly. And BECs are being investigated as potential platforms for building these quantum computers.
So how does this paper's focus on symmetry breaking play into that?
Well, by understanding how symmetry breaking affects BEC, we might be able to control and manipulate BECs in more sophisticated ways.
Meaning we could engineer BECs with specific properties that are tailored for quantum computing applications.
Precisely. For example, we might be able to create more robust and long-lived quantum states within a BEC, which is crucial for building practical quantum computers.
That's pretty exciting. So this research could have a real impact on the development of this game-changing technology.
Absolutely. And it's not just quantum computing. BECs also have potential applications in areas like precision measurement and sensing.
So this is truly groundbreaking work. It's pushing the boundaries of our knowledge and opening up exciting possibilities for both fundamental research and technological innovation.
I completely agree. It's a testament to the power of human curiosity and the endless potential of scientific exploration.
Well, I think we've covered a lot of ground today, from the intricate math of Theorem 1.1 to the mind-bending possibilities of superfluids and quantum computers. It's been a thrilling journey through the world of quantum physics.
It has indeed. And the most exciting part is that this is just the beginning. Who knows what other wonders await us as we continue to explore the mysteries of the quantum world?
That's a great point. There's always more to discover, more to understand, and that's what makes science so captivating, so endlessly fascinating.
I couldn't agree more. The pursuit of knowledge is a journey without end, and it's a journey that's filled with wonder, beauty, and endless possibilities.
Well said. And on that note, I think we'll wrap up this deep dive. A huge thanks to our expert for guiding us through this incredible paper.
It was my pleasure. Always happy to share my passion for physics with such an engaged audience.
And to our listeners, thank you for joining us on this intellectual adventure. We hope you've enjoyed exploring the fascinating world of spontaneous symmetry breaking and its connection to Bose-Einstein condensation. Until next time, keep those quantum gears turning and stay curious.